In this presentation we discuss the mechanics of systems of point masses dealing with the following topics. We will start with the definition of a system of point masses where we describe its equations of motion and classify the forces that can act on such a system. By applying this classification on the equations of motion, we will prove the law of conservation of momentum for a system of point masses, and present some examples illustrating the conservation of momentum in mechanical systems. Then we define a physical quantity describing the state of a rotating system called angular momentum, and prove the law of conservation of angular momentum for a system of point masses, supplying several examples of its conservation. The third law of conservation that we prove here is the law of conservation of energy for a system of point masses by applying the work-energy theorem. As a general example combining more laws of conservation, we will talk about the collisions between homogeneous spheres performing translational motion, and discuss the working principle and the procedure of ballistic pendulum. Finally, we will prove a general principle related to stable systems of point masses in a dynamic equilibrium, known as Virial theorem, describing the relation of different forms of energy in such systems. In many problems related to mechanics we cannot restrict our attention to the analysis of the motion of a single point mass, but we need to study the motion of a system of point masses or bodies approximated by point masses that are simultaneously in interaction with each other. We can consider the system formed by the Sun, the Earth and the Moon, or the Solar System itself as a system of point masses apart from the rotation of the Sun and the planets about their axes. In both cases there are mutual interactions between all the members of the system due to gravitational forces. Two spherical bodies or balls of masses m1 and m2 connected with each other in a fixed stand by springs with negligible mass can also be described as a system of point masses. The forces F1 and F2 are simultaneously exerted on the bodies by the stand, whereas the forces F sub 1 2 and F sub 2 1 represent the interaction between the point masses. Here the mutual interactions between the members of the system are due to the elastic forces produced by the deformation of the springs. Based on these examples, let us consider a system of point masses m1, m2, ellipsis, mn, and denote the position vector of the point mass mi with respect to a reference point O by Ri. Let also Vi denote the velocity of the point mass mi, where the momentum Pi of the point mass is given by the product of its mass mi and its velocity Vi. The net force F bar I acting on the point mass mi is equal to the vector sum of all the forces exerted on the point mass, that is the sum of the forces F sub ij exerted on the point mass mi by the point mass mj, plus any net external force acting on the point mass mi. Then the fundamental equation of dynamics for each point mass governing the motion of the system of point masses is the following. The mass mi times the second-order derivative of the position vector Ri of the point mass mi with respect to the time t, is equal to the net force F bar I acting on the point mass, where the index I of the members of the system runs from 1 to n. The left-hand side of these equations can also be written as the first-order derivative of the momentum Pi of the point mass mi with respect to the time t. These equations state that the acceleration or the rate of change in the momentum of each point mass in the system is given by the net force exerted on the point mass by the rest of the point masses in the interacting system plus the external forces acting on the system. The net forces acting on the point masses do not necessarily point in the directions of the instantaneous velocities of the point masses changing under the effect of these forces, as shown in the figure. Since the fundamental equations are vector equations, they represent 3 times n differential equations for a system of n point masses, where the unknowns are either the coordinates of the position vectors or the components of the momentum vectors as functions of time. If we attach a Cartesian coordinate system to the reference point O, we can expand all the kinematic quantities in Cartesian coordinates. Then the 3 times n fundamental equations state that the mass mi times the second-order time derivatives of the coordinates x, y and z of each point mass mi, are equal to the corresponding Cartesian components of the net force F bar I exerted on the point mass. Similarly, we can express the 3 times n scalar equations as the first-order time derivatives of the Cartesian components of the momentum of the point mass mi, given by the Cartesian components of the force F bar I acting on the point mass mi. If all the instantaneous forces acting on the point masses in the system are known, then an initial value problem can be formulated and we can determine the motion of the whole system. The initial values are either specified by the 3 times n initial coordinates and the velocities of the point masses or their initial momenta. By solving the initial value problem of 3 times n differential equations for the system of n interacting point masses, we can describe the motion of the system in terms of position vectors, velocities or momenta changing in time. Since we need to know the explicit form of the forces describing the interaction between the members of the system and between the system and its environment, first we study the nature of the forces. By applying a proper classification of the forces acting in the system, we will be able to prepare the formulation of general theorems, which provide important information on the motion of the system although they do not determine the motion completely. As already stated, the forces acting on the point masses can be divided into two groups. The internal forces acting between the point masses in the system and the external forces due to bodies outside the system. For example, let us consider the system of the 2 point masses m1 and m2 representing the balls connected to each other and the stand by springs. The external forces acting on the point mass m1 are the weight given by the product of the mass m1 and the gravitational acceleration g, and the force F1 exerted by the stand as the spring connecting the point mass and the stand is stretched. Here the stand does not belong to the system of point masses and it is considered an external body acting on the system. Similarly, the external forces acting on the point mass m2 are its weight given by m2 times g, and the force F2 exerted by the stand pulling the spring used to connect the point mass and the stand. The internal force acting on the point mass m1 is the force F sub 1 2 exerted by the point mass m2 pulling the spring between the point masses, whereas the internal force F sub 2 1 is exerted on the point mass m2 by the point mass m1 pulling the spring from its other end. Considering the general case, we denote the net force of the external forces acting on the point mass mi by Fi, and F sub ij represents the force exerted on the point mass mi by the point mass mj. Then the force term in the right-hand side of the fundamental equations can be written as the sum of the forces F sub ij describing the interaction between the point mass mi and mj for j equals 1 to n, but not equal to I, since the point masses do not act on themselves, plus the external force Fi. As a result, we can formulate the equations of motion of a system of n point masses m1, m2, ellipsis, mn with the position vectors r1, r2, ellipsis, Rn with respect to a reference point O as follows. The mass mi times the second order derivative of the position vector Ri of the point mass mi with respect to the time t, or the first order time derivative of its momentum pi, is equal to the sum of the internal forces F sub ij exerted on the point mass mi by the point mass mj from j equals 1 to n, expect I, plus the net external force Fi exerted on the point mass mi by bodies that do not belong to the system. Here the index I runs from 1 to n. Considering the case of the free and constrained motion of a point mass, we can talk about a free system of point masses such as the solar system, or a rigid system of point masses such as the example with the balls connected with springs where the motion of the point masses is restricted by constraints. 2 point masses m1 and m2 at a fixed distance d sub 1 2, called rigid rotor, also form a rigid system of points, where the only constraint is the one stating that the distance between the 2 point masses is constant during the motion of the rotor. With respect to a given reference point O, the position vectors r1 and r2 of the 2 point masses can be represented by their Cartesian coordinates in a coordinate system attached to the reference point, and we can express this constraint in a mathematical form. That is the sum of the square of the differences between the Cartesian coordinates of the position vectors of the point masses is equal to the square of the distance d sub 1 2 between the point masses m1 and m2. The degrees of freedom F for the motion of 2 point masses is 2 times the number of the coordinates describing their instantaneous positions, that is F equals to 6. The one constraint imposed on the motion of the rigid rotor reduces its degrees of freedom to 5. We have already seen that freely moving rigid bodies have a degrees of freedom of 6 since 3 points of the body are needed to determine its position and orientation which are given by 9 coordinates, and 3 constraints state that the distances between these points are constant. Rigid bodies can be considered as rigid systems of point masses, and in general, any system combined from rigid bodies forms such a system where constraints are imposed between the points of the different rigid parts in the system. Although this approach cannot be applied in a direct form for systems of infinitely many degrees of freedom, such as liquids, the theorems proven for systems of point masses in the next section will still hold for systems of infinitely many degrees of freedom. Besides dividing forces into internal and external forces, we can use other criteria to classify the forces exerted on rigid systems of point masses. We can talk about the aforementioned free forces acting on a given system such as weight or gravitational force, elastic force, or frictional force, and constraint forces replacing constraints imposed on motion that are not explicitly given, for example the contact surfaces of rigid bodies sliding or rolling over each other. As a result, we can write the equations of motion of a system of point masses in the form stating that the mass mi times the second order time derivative of the position vector Ri of the point mass mi in the system, is equal to the vector sum of the net force F sub naught I of the free forces acting in the point mass mi, and the net force F naught prime of the constraint forces exerted on the point mass. Both free forces and constraint forces can be internal forces and external ones. For example, the force exerted on the tennis ball by the ground while is at rest on the ground is an internal constraint force, but if we consider the ball itself as a system, then the force produced by the ground will be an external constraint force acting on the system. These classifications of forces enlisted here are crucial when we formulate general theorems on the motion of systems of point masses. Before presenting these general theorems, we note that the scalar form of the equations of motion of a system of point masses can also be expressed in curvilinear coordinates. We already defined the cylindrical coordinate system, which we apply to describe the kinematic quantities of a system of point masses. If we attach such a coordinate system to the reference point O, we will able to represent the position vector r of any point mass in the system by its cylindrical coordinates, such as the radial distance ρ of the point mass from the z-axis, the polar angle phi, and the coordinate z of the point mass. Other kinematic quantities, like the velocity v and the acceleration a of the point masses, and the force F bar acting on the point masses, can also be described by their components written in a cylindrical coordinate system. The left-hand side of the equations of motion depends on the acceleration a of the point masses, that is the first-order time derivative of their velocity v or the second-order time derivative of their position vector r. When we studied kinematics, we determined the components of the acceleration of a point mass in a cylindrical coordinate system. We found that the radial component of the acceleration a is given by the second-order time derivative of the radial distance ρ, minus ρ times the square of the first-order time derivative of the azimuthal angle phi. The azimuthal component of the acceleration is equal to ρ times the second-order time derivative of phi, plus 2 times the first-order time derivative of ρ times the first-order time derivative of phi. The z component of acceleration is simply given by the second-order time derivative of the z-coordinate. These expressions can be substituted into the components of the equation of motion for each point mass in the system. Then the radial component of the equation of motion of the point mass mi states that the mass mi times the radial component of the acceleration of the point mass is equal to the radial component of the net force F bar I acting on the point mass mi. Similarly, the azimuthal component of the equation of motion states that the mass mi times the azimuthal component of the acceleration of the point mass is equal to the azimuthal component of the force F bar I acting on the point mass mi. The z component of the equation of motion is the same as in the case of the Cartesian coordinates, that is mi times z double dot is equal to the z component of the force F bar I acting on the point mass mi. Although the radial and azimuthal components of the equations of motion are more complicated than the equations of motion written in Cartesian coordinates, they can be simplified if the motion of the system of point masses exhibits a cylindrical symmetry which the cylindrical coordinate system is adapted to. For example, if the radial distances ρ I of the point masses in the system from the z-axis are constant during their motion, that is, they move over cylindrical surfaces around the z-axis, we can drop the radial component of the equation of motion, and omit the term with the time derivative of the radial coordinate ρ I in the azimuthal component of the equations of motion. The other curvilinear coordinate system frequently used in mechanics is the spherical polar coordinate system, which can also be applied for a system of point masses to derive the scalar form of the equations of motion of the system. By attaching a spherical coordinate system to the reference point O, we can express the position vectors of the point masses in terms of the radial coordinate r, the polar angle theta, and the azimuthal angle phi. The velocity and the acceleration of the point masses together with the force acting have the corresponding expressions in spherical polar coordinates as well. As in the case of the cylindrical coordinate system, we determine the acceleration of a point mass in a spherical coordinate system. The radial component of the acceleration is given by the second-order time derivative of the radial coordinate r, minus r times the square of the first-order time derivative of the polar angle theta times the square of the sine of the azimuthal angle phi, minus r times the square of the first-order time derivative of phi. The polar component of the acceleration is equal to r times theta double dot times sine phi, plus r dot times theta dot times sine phi, plus 2 times r times theta dot times phi dot times cosine phi. Finally, the azimuthal component of the acceleration is given by r times phi double dot, plus 2 times r dot times phi dot, minus r times the square of theta dot times sine phi times cosine phi. As in the case of the components written in cylindrical coordinates, the components of the acceleration in spherical coordinate system contain the second-order time derivative of the corresponding coordinate, but they are functions of the first-order time derivative of the other coordinates as well. We can substitute the expressions obtained for the accelerations of the system of point masses into the equations of motion for the radial, polar, and azimuthal coordinates, where the left-hand side is equal to the corresponding components of the net force F bar I acting on the point mass mi in the spherical polar coordinate system. Although these equations are even more complicated than the equations written in cylindrical coordinates, they can be simplified if the motion of the point masses in the system has a spherical symmetry. For any system of point masses moving such that their distance from a given point is constant, the coordinate system can be adapted to this symmetry. As a result, the radial equations can be dropped, and the time derivatives of the radial coordinates will vanish, reducing the equations of motion to the terms containing the derivatives of the angular coordinates. Now we formulate the principle of conservation of momentum for a system of point masses. Let us consider a system that consists of only 2 point masses m1 and m2, where the instantaneous velocities of the point masses are v1 and v2 while the net force f-bar1 and f-bar2 are exerted on them. The momenta p1 and p2 of the point masses are given by the products of the masses m1 and m2, and the velocities v1 and v2. Then the system has two equations of motion stating that the derivative of the momentum p1 of the point mass m1 with respect to the time t is equal to the net force f-bar1, which is equal to f sub 1 2 plus the force f1, and that the time derivative of the momentum p2 of the point mass m2 is given by the net force f-bar2, which is equal to the force f sub 2 1 plus the force f2. Here the force f sub 1 2 is the force exerted on the point mass m1 by the point mass m2, whereas f1 is the net external force acting on the point mass m1. Similarly, the force f sub 2 1 is the force exerted on the point mass m2 by the point mass m1, and f2 is the net external force acting on the point mass m2. If we add the two equations together, then we obtain an expression stating that the time derivative of the sum of the momenta p1 and p2 is equal to the sum of the internal forces f sub 1 2 and f sub 2 1, plus the sum of the external forces f1 and f2. Now we can apply Newton's third law for action and reaction, stating that every action has an equal and opposite reaction. That is, the force f sub 1 2 is equal to minus the force f sub 2 1. As a result, the first sum in the right-hand side vanishes, and we conclude that the time derivative of the sum of the momenta p1 and p2 is equal to the vector sum of the external forces f1 and f2. We will obtain the same result for a system of n-point masses m1, m2, ellipsis, mn, where the net forces f-bar I are exerted on the members of the system, and the momentum pi of the point mass mi is given by the mass mi times the velocity vi of the point mass. As already seen, the equations of motion for the general case state that the time derivative of the momentum pi of the point mass mi is equal to the net force bar fi acting on the point mass, where the net force can be decomposed into the sum of the internal forces f sub ij from j equals 1 to n, expect I, plus the net external force fi. Here the force f sub ij is the force exerted on the point mass mi by the point mass mj, whereas the force fi is exerted on the point mass mi by external bodies. As in the case of the 2 point masses, we can add the n equations of motion together, obtaining the vector sum of the time derivatives of the momenta from I equals 1 to n on the left-hand side, and the double sum of the internal forces and the sum of the external forces from I equals 1 to n on the right-hand side. By adding the equations of motion, the internal forces cancel each other out in the vector sum due to Newton's law of action and reaction, which states that the force F sub ij is equal to minus the force F sub ji. Since the force F sub ij is the force exerted on the point mass mi and the force F sub ji is the force exerted on the point mass mj, they act on different bodies, so they cannot cancel out. However, they do in the sum of the equations of motion of the system involving all the point masses and therefore all the forces acting on these point masses. This statement can be demonstrated if we group the members of the double sum of the internal forces such that its first partial sum contains only those forces where the second index is greater than the first one, and its second partial sum where the pairs of indices seen in the first partial sum are reversed. Since the first terms in the partial sums are equal but opposite, their vector sum cancel each other out. Similarly, the second terms in the partial sums cancel out, and the rest of the pairs in the partial sums cancel out as well. As a result, the vector sum of the two partial sums is equal to 0, and the double sum of the internal forces in the right-hand side of the equations of motion vanishes. Then we can state that the sum of the derivatives of the momenta pi of all the point masses mi in the system from I equals 1 to n with respect to the time t, is equal to the vector sum of the external forces Fi acting on the point masses mi from I equals 1 to n. We also express the left-hand side as the time derivative of the sum of the momenta pi of the individual point masses from I equals 1 to n, which helps us to formulate the result in the following form. For a system of point masses m1, m2, ellipsis, mn, we can define the total momentum p by the vector sum of the momenta pi of the point masses mi from I equals 1 to n. Therefore the total momentum p of the system is given by the sum of the product of the masses mi and the velocities vi of the point masses from I equals 1 to n. Similarly, the net force F of all the external forces Fi acting on the system of point masses is given by the vector sum of the external forces Fi acting on the individual point masses from I equals 1 to n. Now we can write the sum of the equations of motion in a general form stating that the derivative of the momentum p of a mechanical system with respect to time is equal to the net force F of all external forces acting on the system. This statement holds for any problem in mechanics, and this result describes the equation of motion of an arbitrary mechanical system. In the case of a system of point masses, we can still state that the time derivative of the sum of the product of the mass mi and the velocity vi of the point mass mi from I equals 1 to n is equal to the vector sum of the external forces Fi acting on the point masses mi from I equals 1 to n. We note that the momentum p of a mechanical system, also called linear momentum or sometimes translational momentum, indicating that the nature of its definition is related to spatial translations. Since the momentum p of a point mass is defined by the product of its mass m and its instantaneous velocity v, its points in the direction of its velocity, and it is related to an infinitesimal translation of the moving point mass in this direction per an infinitesimal time. The terms linear and translational help to contrast this quantity with another type of momentum that will be introduced for rotations. As a result, the equation of motion for mechanical systems describes the rate of change of the linear momentum of the system given by the net force exerted on the system. Then we have to clarify what kind of translation is described by the total momentum in the case of a system of point masses. In fact, by adding the n equations of motion of the system together, we have reduced the number of equations to one, that is, we combine them into one equation of motion. Although the resultant equation does not describe the time evolution of the individual members of the system, we can associate the total momentum of the system with some quantities determined by the instantaneous positions of the point masses in the system. In order to determine these quantities, we use the sum of the equation of motion written in the terms of the velocities vi of the point masses mi in the system, and express the velocity vi in the sum of the equations of motion as the time derivative of the position vector Ri of the point mass mi. Then we can write that the second-order derivative of the sum of the product of the mass mi and the position vector Ri from I equals 1 to n is equal to the net force F of the external forces acting on the system of point masses. Now we can introduce the total mass m of the system as the sum of the individual masses mi of the particles in the system, and multiply and divide the left-hand side of the equation of motion of the system at the same time by the total mass. In the parentheses we recognize the center of mass Rc defined for the system of point masses m1, m2, ellipsis, mn by 1 over the total mass m, times the sum of the mass mi times the position vector Ri from I equals 1 to n. The resultant form of the equation of motion states that the total mass m of the system times the second-order derivative of the position vector Rc of the center of mass of the system with respect to the time t, is equal to the net force F given by the vector sum of the external forces acting on the system. This is also called the center of mass theorem, that can be phrased as follows. The center of mass of a mechanical system moves as if its total mass were concentrated at the center of mass, and the net force of all the external forces acting on the system were applied there. This theorem shows that the internal forces of the system do not have an effect on the motion of the center of mass of the system or the total momentum of the system. The kinematic quantities describing the motion of the center of mass of the mechanical system are its position vector Rc and its time derivative, that is, the instantaneous velocity Vc of the center of mass. Instead of the velocity, the total momentum p can be used to describe the motion, which is equal to the momentum pc defined by the total mass m of the system, times the velocity Vc of the center of mass. As a result, we can replace a rigid body with its mass concentrated at its center of mass in many cases, since the body moves as a point mass m under the influence of a net external force F. We stress again that the equation of motion governing the motion of the center of mass of a rigid body does not describe the motion of the individual points of the body. For example, if a force couple is applied on a rigid body, then it will not have an effect on the motion of its center of mass, as its net force of the force couple exerted on the body is zero, but it can rotate the body about its center of mass. We can write the equation of motion of the system as a chain of equalities stating that the time derivative of the total momentum defined as the sum of the mass mi times the velocity vi for the point mass mi from I equals 1 to n, is equal to the vector sum of the external forces Fi acting on the point masses mi from I equals 1 to n, which is the net external force F acting on the system. This expression tells us if the net external force F vanishes, then the total momentum p of the system is constant, that is, the acceleration of the center of point mass is equal to zero and its velocity is constant. This statement follows from the fact that the constant total momentum p of the system is given by the sum of the mass mi times the velocity vi of the point mass mi from I equals 1 to n. Since this sum is constant, the velocity of the center of mass is constant as well. This result is the law of the conservation of momentum for a mechanical system, stating that if external forces do not act on a mechanical system or the net force of these forces vanishes, then the momentum of the system is constant, that is, its center of mass remains at rest or in a uniform rectilinear motion. If no external forces act on a mechanical system, then we call it a closed system. Then the theorem states that the momentum is conserved in closed mechanical systems. In order to illustrate the law of conservation of momentum, we present two laboratory experiments. In the first one, we insert a compressed spring between two laboratory carts where a thread is attached to the two ends of the spring to prevent the spring from expansion. The system formed by the carts of masses m1 and m2 and the spring of negligible mass are at rest on a horizontal plane. By cutting the thread, we let the spring expand and push the carts in opposite directions. If we measure the velocities v1 and v2 of the carts, then we will find that the magnitude of the velocities is inversely proportional to the masses of the carts. The external forces acting on the system are the weights of the carts given by the product of the mass m1 and the gravitational acceleration g, and the mass m2 times g. The reaction to this action consists of the constrained forces F1' and F2' exerted on the carts by the horizontal plane, with the same magnitudes but opposite directions. Further external forces are the frictional forces between the wheels of the carts and the surface of the plane. If we can neglect the friction, then the net external force acting on the system given by the vector sum of the action and reaction forces vanishes. As a result, we have a closed mechanical system where the total momentum is constant. Since the momentum p is equal to 0 in the initial state of the system at rest, it must remain 0 during motion. Therefore, the momentum p given by the mass m1 times the velocity v1, plus the mass m2 times the velocity v2 is equal to 0. This vector equation can be reduced to a single scalar equation stating that m1 times the magnitude of v1 minus m2 times the magnitude of v2 vanishes because the velocities of the carts point in opposite directions. Then we obtain that the magnitude of the velocity v1 divided by the magnitude of the velocity v2 is equal to the ratio of the mass m2 to the mass m1. Thus the velocities of the carts are indeed inversely proportional to their masses. We can formulate this resultant in the terms of the motion of the center of mass by stating that the position of the center of mass of the system does not change during motion, that is, its center of mass remains at rest. However, if we use an inclined plane with the inclination angle alpha in the experiment, the center of mass will move with the acceleration of g times sine alpha along the plane. In the second experiment, we mount a pendulum on a laboratory cart of mass m1 which is at rest on a horizontal plane. If the initial position of the pendulum is at the point P and we let its bob of mass m2 free, then it will start to swing and the cart will be set in motion. While the pendulum swings, the cart always rolls back and forth in the opposite direction of the swing of the pendulum. The forces exerted on the cart in the horizontal direction are the frictional force produced by the wheels of the cart and the horizontal component of the constraint force acting downward and toward the bob, which is the reaction to the tension force that results from the string pulling upon the bob. The horizontal component of the tension force is the only force exerted on the pendulum in the horizontal direction. If we neglect friction, then no external forces are applied on the system formed by the cart and the pendulum in the horizontal direction. Since the internal forces are equal and opposite, the momentum of the system is conversed in the horizontal direction. As a result, the momentum of the system remains 0 during motion and its center of mass stays at rest. In a coordinate system oriented along the horizontal plane, the x-component of the vanishing momentum p of the system can be written as the mass m1 times the x-component of the velocity v1 of the cart, plus the mass m2 times the x-component of the velocity of the pendulum, which is equal to 0. Then we have the equation stating that m1 times the absolute value of v1 is equal to m2 times the absolute value of v2. The forces acting on the cart in the vertical direction are the vertical component of the reaction of the tension force, the gravity, and the reaction force produced by the plane on which the cart rolls. The first force is an internal force and the last two forces are external ones, and the net force of these three forces are 0, that is, the vertical component of the momentum of the cart is 0 with vanishing velocity in the vertical direction. The vertical forces acting on the pendulum are the vertical component of the torsion force and the gravity. The first force is a changing internal force while gravity is a constant external force, and their net force does not vanish. As a result, the pendulum has a non-zero momentum and velocity in the vertical direction periodically changing in time. If the system also includes the Earth, the action and reaction forces between the cart with the pendulum and the Earth cancel out in the vertical direction. Then the momentum of the whole system is conserved in the vertical direction, and the center of mass of the system has a fixed position in the vertical direction as well. We can also mention some examples illustrating the law of the conservation of momentum. In our first example, we consider the orbital motion in the solar system. Any astronomical object that exists outside the solar system exerts only a very small gravitational force on the Sun, the planets, and the other members of the solar system. As a result, our solar system can be considered as a closed system, at least to first approximation, and its center of mass is either at rest or in a uniform linear motion with respect to any inertial frame. We note that the Sun itself is also moving along a curve around the center of mass or the barycenter of the solar system, and the barycenter is sometimes inside the body of the Sun and sometimes outside it, but still in its close vicinity. The second example is an exploding grenade thrown in the air. If the grenade explodes mid-air, the internal forces causing the explosion do not have any effect on the motion of the center of mass of the system, that is on the grenade and the dispersing fragments of the grenade. The center of mass of the system moves along the same parabola in vacuum as the grenade before its explosion. In the air, the motion of the center of mass will be different due to the drag forces acting on the grenade and its fragments in a different way. A high jumper or a long jumper can also be a good example for the role of external and internal forces played in the conservation of momentum of the jumping athlete. High jumpers and long jumpers apply a force on the ground greater than their weights pointing slantwise downward. The reaction to this action is an external force exerted by the ground with its vertical component pointing upward, which causes the raise of the athlete from the ground. The horizontal component of the reaction is the static frictional force causing the horizontal motion of the athlete. In the air, the high jumper or the long jumper cannot change his or her motion along a parabola, but the athlete can gain a better orientation of his or her body by applying internal forces. The body of the high jumper is brought into a vertical position when he or she jumps over the crossbar, whereas long jumpers extends their legs before landing on the sand. Another example of the conservation of momentum is the system formed by a cannon and its projectile. If friction is neglected when the projectile leaves the barrel of the cannon, then no external forces are exerted on the system in horizontal direction and its momentum is conserved in that direction. As a result, we can apply the equation stating that the mass m1 of the recoiling barrel times the horizontal component of its velocity v1, plus the mass m2 of the projectile times the horizontal component of the velocity v2 of the projectile is equal to 0. Here the velocities v1 and v2 are measured with respect to the Earth as an inertial frame of reference which we attach a coordinate system. The projectile leaves the barrel with the velocity u with respect to the barrel in the direction opposite of the x-axis, and the velocity of the barrel is denoted by v. Then we can express the velocity components of the barrel and the projectile measured in the inertial frame as v, and minus the difference between u and v. By inserting these expressions into the equation formulating the conservation of momentum, we can write that m1 times v, minus m2 times u, plus m2 times v vanishes. The velocity v of the recoiling barrel can be expressed as the ratio of the mass m2 of the projectile to the sum of the mass m1 of the barrel and the mass m2, times the velocity u of the projectile with respect to the barrel. Besides the recoil of cannons or guns, these equations describe other examples illustrating the law of the conservation of momentum, like someone with the mass m2 jumping from a trailer of mass m1, or throwing a stone of mass m2 with the relative velocity u in the direction opposite of the x-axis while standing on the trailer. We can write the law of the conservation of momentum in the moving frame and express the velocity u of the trailer from it. Since the mass of the jumping person or the stone thrown away from the trailer is much smaller than the mass of the trailer, the velocity v of the trailer is also much smaller than the velocity u of the person or the stone. However, this process with stones stored on the trailer can be repeated several times following the one after the other fast enough to gradually increase the velocity of the trailer. This is the principle behind propulsion, applying Newton's third law of motion and the law of the conservation of momentum. In general, propulsion means to push forward or drive an object forward where some mechanism produces the thrust pushing the object forward. Instead of throwing stones, a gas or some working fluid can be expelled from the object to gain thrust, which can be demonstrated by a rubber balloon filled with air. The pressurized air rushes out the open end of the inflated balloon, and as a reaction to this action the balloon rocket is pushed into the opposite direction. We finish the list of examples with the discussion on the principle of rocket propulsion. Rockets are propelled by the reaction produced by ejecting burned fuel gases, also called propellant, where the action in Newton's third law of motion is the expulsion of high-speed gas from the engine of the rocket, and the reaction is the forward movement of the rocket. Let us assume that the rocket has the mass m1 and the velocity v sub 1x in the direction of the x-axis at a given instant of time t, that is both its mass and speed are functions of time. For the mass we will drop the subscript 1, and we denote the x component of the velocity by v. Now an infinitesimally small amount of burned fuel of mass m2, written in the form -dm, is exhausted out the nozzle of the rocket with the velocity u with respect to the rocket in the direction opposite of the x-axis. Then the velocity of the ejected gas is equal to minus the difference between the relative velocities u and v. After the exhaustion of the small amount burned propellant, the mass of the rocket becomes m plus dm, which is less than the mass m because dm is negative. At the same time the velocity v of the rocket is increased by dv. As a result, the component of the momentum of the rocket in the x direction is equal to the product of its mass m decreased with minus dm and its velocity increased with dv. The momentum of the burned fuel after its expulsion is given by minus m2 times the difference between u and v, or dm times the difference between u and v. If there are no external forces acting on the system formed by the rocket and the ejected material, then the law of conservation of momentum states that the product of m plus dm and v plus dv, plus dm times the difference between u and v is equal to the momentum of the system at the initial time, that is the mass m times the velocity v. We can factor out the terms in the parentheses and drop the terms from the result which cancel out each other. Then we obtain the equation stating that m times dv, plus dm times dv, plus dm times u, is equal to m times v. Since the second term in the left-hand side can be neglected in comparison with the other terms, we can also drop it and express the differential of v from the equation as minus the infinitesimal change of m over m, times u. This result describes the increase in the velocity of the rocket after the high-speed gas of mass dm is expelled from the rocket during an infinitesimal time dt. If we integrate this differential equation from the time of the launch to a given instant of time t and assume that the speed of the gas is constant with respect to the rocket, then we obtain the ideal rocket equation, where gravity, the drag forces and the rotation of Earth are ignored. This formula derived independently by Moore in 1810 and Tsiolkovsky in 1898 tells us that in the absence of external forces, a rocket with the initial or full mass mf gains the velocity delta v during the time t, which is proportional to the ejection velocity u of its burned fuel and the logarithm of the ratio of its full mass to its instantaneous mass. After burning the total amount of fuel carried by the rocket in the final stage, the mass of the rocket will have been reduced to its empty mass me, where the maximum increase delta v in the velocity of the rocket is given by the gas velocity u, times the logarithm of the ratio of its initial or full mass to its final or empty mass. If we introduce the rocket's mass ratio defined by the full mass mf over the empty mass me reached at the time te of the end of the burnout of the propellant, then we can write delta v as u times the logarithm of the rocket mass ratio. Here the mass ratio can be expressed as the exponential of the ratio of the maximum speed of the rocket to the speed of the gas exhausted from its nozzle. In other words, this formula gives the mass ratio needed for a given rocket engine producing a thrust with the velocity u, in order to reach the maximum velocity delta v for the rocket. Let mu denote the mass flux through the nozzle of the rocket, that is minus the time derivative of the instantaneous mass m of the rocket, and let us assume that the mass flux is constant. Since the infinitesimal change dm in the mass of the rocket is negative, the mass flux mu is positive. Then the instantaneous mass m of the rocket can be written as its initial or full mass mf, minus mu times the time t until the total amount of the propellant is consumed. By substituting this equation into the expression obtained for the instantaneous velocity v of the rocket, we can write v as minus u times the logarithm of the ratio of the difference between mf and mu times t to mf. If we do not neglect gravity, then the instantaneous velocity of the rocket in a vertical flight is given by minus the gas velocity u times the logarithm of 1 minus the ratio of the mass flux mu to the full mass mf times the time t, minus the magnitude of the gravitational acceleration g times the time t. In order to obtain the height reached after the time t by the rocket, we only need to integrate the velocity v from 0 to the time t. At the time te denoting the end of the burnout process of the propellant, the rocket reaches the height, where its propulsion stops and the rocket will move as a projectile. If we use the formula describing the maximum height of a vertical projectile to determine the maximum height reached by the rocket, then we can write it as the height h of the rocket at the time of the end of the burnout of its fuel, plus the square of the maximum velocity delta v gained during the propulsion divided by 2 times the gravitational acceleration g. For example, in the case of the Phi-2 rocket, the relative velocity u of the ejected burnt fuel is about 2 km per second, whereas the full mass of the rockets is about 13,000 kg and the empty mass is 4,000 kg. Then the mass ratio of the rockets is equal to 3.25, and the theoretical maximum limit of the velocity of the rocket is equal to 2.4 km per second. Because it takes about 70 seconds for the rocket engine to burn 9,000 kilograms fuel, the mass flux is given by 0.01 times the full mass mf per second. By inserting these data into the rocket equation and integrating the velocity from 0 to the burnout time, we obtain 1.72 km per second for the maximum velocity and the height 43.8 km reached by the rocket at that point. After all the fuel is consumed, the rocket will move as a projectile thrown upwards from the height of 43.8 km with the initial velocity of 17.2 km per second. If we substitute these values into the equation for the projectile motion, we obtain the maximum height of 192 km that the Phi-2 rocket can reach. This height is much smaller than the low Earth orbit starting at the altitude of 800 km, which requires a delta V, and in turn the rocket mass ratio larger than those can be achieved in a single rocket stage. An approach using multi-stage design was first suggested by Tsiolkovsky to overcome this limit by dividing the increment delta V and velocity into stages. A multi-stage rocket is a launch vehicle that uses two or more rocket stages, each of which contains its own engines and propellant. When the first stage propellants are used up, that stage is detached from the remaining parts of the rocket and falls back. As each lower stage drops off and the succeeding stage starts to accelerate the rest of the rocket, the vehicle is still traveling near the burnout speed. The most powerful three-stage rocket is the Saturn V heavy lift vehicle that ever took a flight successfully, and carried the Apollo spacecraft, allowing mankind to land on the Moon. Besides the law of conservation of momentum, another general law follows from the equations of motion of a system of point masses that determines the relation between the forces acting in the system and the momenta associated with the torques produced in the system. Let us start our discussion with a system of 2 point masses m1 and m2 with the position vectors r1 and r2 with respect to a reference point O, where the velocities of the point masses are v1 and v2, and their momenta are given by m1 times v1 and m2 times v2. The forces F sub 1 2 and F sub 2 1 are the internal forces acting in the system, and the forces F1 and F2 are external ones applied on the system. Then the first equation of motion of the system states that the derivative of the momentum of the point mass m1 with respect to the time t is equal to the internal force F sub 1 2 plus the external force F1, both acting on the point mass m1. The second equation of motion similarly states that the time derivative of the momentum p2 of the point mass m2 is given by the internal force F sub 2 1 plus the external force F2, both acting on the point mass m1. Here the internal force F sub 1 2 is exerted on the point mass m1 by the point mass m2, and the internal force F sub 2 1 is exerted on the point mass m2 by the point mass m1. Now we take the cross product of the position vector r1 with the first equation of motion, and the cross product of the position vector r2 with the second one. If we add these two equations, then we obtain one equation stating that the cross product of r1 and the time derivative of p1, plus the cross product of r2 and the time derivative of p2, is equal to r1 cross f1 plus r2 cross f2, plus r1 cross f sub 1 2 plus r2 cross f sub 2 1. By applying Newton's third law of action and reaction for the last two terms in the right-hand side, we can write the sum of them as r1 cross f sub 1 2 minus r2 cross f sub 1 2, which gives the cross product of the difference between the position vectors r1 and r2, and the internal force F sub 1 2. Since the vector r1 minus r2 points from the point mass m2 to the point mass m1, it will coincide with the line of action of force F sub 1 2 acting between the point masses. As a result, the cross product in the right-hand side of the equation vanishes, and the sum of the cross products of the position vectors and the equations of motion reduces to the equation stating that r1 cross the time derivative of p1, plus r2 cross the time derivative of p2, is equal to r1 cross f1 plus r2 cross f2. We can follow the same procedure in the general case, and we can prove that for a system of point masses m1, m2, ellipsis, mn at the positions r1, r2, ellipsis, rn, the following equation holds. The sum of the cross product of the position vector ri and the time derivative of the momentum pi of the point mass mi from I equals 1 to n, is given by the sum of the cross product of the position vector ri and the external force Fi acting on the point mass mi from I equals 1 to n. The left-hand side can be transformed into another form, if we apply Leibniz's rule for the time derivative of the cross product of the vectors ri and pi, which gives the time derivative of ri cross pi, plus ri cross the time derivative of pi. By definition, the time derivative of the position vector ri is equal to 1 over the mass mi times the momentum pi, that is the first term in the right-hand side vanishes. Now we can substitute this result into the left-hand side of the sum of the cross products of the position vectors of the point masses with the equations of motion for the system. Then we obtain a new equation stating that the time derivative of the sum of the cross product of the position vector Ri of the point mass mi and its momentum pi from I equals 1 to n, is equal to the sum of the cross product of the position vector Ri and the external force Fi acting on the point mass mi from I equals 1 to n. In the left-hand side we see the derivative of an expression with respect to the time, which contains the cross product of the position vector and the momentum of a point mass. We already defined the torque tau produced by a force F acting on a rigid body at a point P described by the position vector r with respect to the center of rotation O, which is the cross product of the position vector r and the force F. The definition can also be applied for a point mass at the point P when we examine its instantaneous rotation about the point O. Similar to the definition of torque also called moment of force, we can introduce the moment of momentum called angular momentum, a rotational counterpart to linear momentum. The angular momentum L of a point mass m of momentum p with respect to a point O is defined by the cross product of the position vector r pointing from the point O to the point mass, and the momentum p. The angular momentum is a vector perpendicular to the position vector and the momentum with the orientation given by the right-hand rule of the cross product. The unit of the angular momentum is given by the product of the unit of length and the unit of momentum, that is the unit of mass times the unit of length to 2 times the unit of time to -1, which is equal to kilogram times meter squared per second in SI units. In the case of a system of point masses, we can write the angular momentum Li of the point mass mi with respect to the reference point O as the cross product of the position vector Ri of the point mass and the momentum pi of the point mass. Similarly, the torque tau I produced on the point mass mi by the force Fi is equal to the cross product of the position vector Ri and the force Fi. Then we can define the total angular momentum L of the system as the vector sum of the angular momenta Li of the point masses mi from I equals 1 to n, and the total torque tau produced on the system can be written as the vector sum of the torques tau I of the point masses mi from I equals 1 to n. If we apply the definitions of the total angular momentum of the system of point masses and the total torque applied on the system for the sum of the cross products, then we obtain the following theorem. The derivative of the angular momentum L of a mechanical system with respect to the time t is equal to the torque tau produced by the net force of the external forces acting on the system, where both the angular momentum and the torque are determined with respect to the same reference point O. This theorem holds for any mechanical system, and for a system of n-point masses it can be written as the equation stating that the time derivative of the sum of the mass mi times the cross product of the position vector Ri and of the velocity vi of the point mass mi from I equals 1 to n, is given by the sum of the cross product of the position vector Ri and the external force Fi acting on the point mass mi from I equals 1 to n. As a consequence of the theorem, if the torque tau produced by the net force of the external forces applied on the system vanishes, then the total angular momentum of the system is constant. In the case of a system of point masses, the vanishing sum of the cross product of the position vectors Ri of the point masses mi and the external forces Fi acting on these point masses makes the sum of the mass mi times the cross product of the position vectors Ri and the velocities vi of the point masses constant. This is the law of conservation of angular momentum for any mechanical system, stating that if no external forces act on a system or the torque produced by the external forces acting on a mechanical system vanishes, then the angular momentum of the system is constant. In other words, the angular momentum of a closed system, that is a system in which no external forces are applied, is conserved. As a special case, we can consider a system that consists of a single point mass at the point P described by the position vector R relative to the reference point O, where the point mass has the instantaneous velocity v under the influence of the force F. Then the law states that the cross product of the position vector r and the velocity v of the point mass is constant if the cross product of its position vector r and the force F acting on the point mass is equal to 0. This statement is the reformulation of the law of constant areal velocity, which we already proved in the discussion on elliptic and planetary motion. We saw that the law of constant areal velocity is related to central forces, that is, forces acting on a particle always directed towards or opposite to a fixed point O and given by the magnitude F depending on the distance r of the particle from the fixed point, times the position vector r of the particle relative to the fixed point O. In the case of central motion, the cross product of the position vector r and the force F vanishes, that is, the torque produced on the point mass by the central force is equal to 0. Then the principle of conservation of angular momentum tells us that the areal velocity with the magnitude given by the area A swept out per unit time by the position vector r of a point mass moving along a curve is constant. This is due to the fact that the areal velocity, that is the time derivative of the area vector with the magnitude of the area A and the direction normal to the instantaneous plane of the orbit of the point mass, is given by 1/2 times the cross product of the position vector r and the velocity v of the point mass with respect to the point O. Then the central force acting on a point mass with the constant cross product of r and v gives a constant areal velocity for the point mass. As a result, we can conclude that the law of constant areal velocity is a consequence of the conservation of angular momentum in the case of central motion. Now we examine the relationship between the angular momentum of any rotating mechanical system and the inertial properties of the system with respect to its rotation. Let us consider a rigid body rotating about a given axis with the angular velocity omega, and determine the component of the angular momentum of the body parallel with the axis of rotation. If we choose an arbitrary point O on the axis of rotation as a reference point and attach a coordinate system to the reference point such that its z-axis is the axis of rotation, then we need to determine the z component of the angular momentum L of the rotating body. We already approximated rigid bodies as systems of point masses, where we decompose the body into the set of mass elements represented by the system of n point masses mi with fixed distances from each other, where our I and vi denote the position vector and the velocity of each point mass mi with respect to the reference point O. Then in the approximation using a system of point masses, the angular momentum L of the rotating body with respect to the reference point O can be written as the sum of the angular momenta Li of the point masses mi with respect to the reference point O from I equals 1 to n, where Li is given by the mass mi times the cross product of the position vector Ri and the velocity Vi of the point mass mi. Since the instantaneous position vector Ri of the rotating point mass is perpendicular to its instantaneous velocity Vi, the magnitude of their cross product perpendicular to the plane spanned by them is equal to the length of the position vector times the magnitude of the velocity, and the magnitude of the angular momentum Li is given by mi times the product of the length of Ri and the magnitude of Vi. In order to determine the component of the angular momentum L of the rigid body parallel with the axis of rotation, we need to compute the z component of the angular momentum Li. If the polar angle theta I denotes the angle between the direction of the angular momentum Li and the z-axis, its component parallel with the axis of rotation can be written as the projection of Li onto the z-axis, that is as mi times Ri times Vi, times cosine theta I. We can also write the velocity Vi of the rotating point mass mi as the product of the angular velocity omega and the distance di between the point mass mi and the z-axis. Because the angle between the distance vector di and the position vector Ri is a parallel angle of the angle theta I, the distance di can be expressed as the length of the position vector Ri times cosine theta I. As a result, the z component of the angular momentum Li is equal to the mass mi times the square of the distance di, times the angular velocity omega. We can introduce the angular velocity vector omega with the magnitude of the angular velocity of the rigid body rotating about the z-axis, denoted by omega z, and with the direction of the axis of rotation or the unit vector Ez. The magnitude of the angular velocity vector can be either positive or negative depending on the direction of rotation of the body. Then in the general case, the z component of the angular momentum Li given by plus or minus mi times ds squared times omega, is equal to the mass mi times the square of the distance di, times the z component of the angular velocity vector omega. Now we are able to determine the z component of the angular momentum of the rotating body given by the sum of the angular momenta Li of the point masses mi from I equals 1 to n, and write it as the z component of the angular velocity vector z describing the rotation of the body, times the sum of the point mass mi used to approximate a given part of the body, times the square of the distance di of the point mass mi from the axis of rotation from I equals 1 to n. In this expression the component of the angular momentum parallel with the axis of rotation is equal to the product of omega z describing the rotation, and a sum depending only the mass distribution of the system of point masses approximating the body around its axis of rotation. We call this sum denoted by capital I, the moment of inertia of the system of point masses or the rigid body with respect to the axis of rotation z. Its definition shows that the greater the mass of the point masses and the greater their distance from the axis of rotation, the greater the moment of inertia of the point masses distributed around the axis. In Cartesian coordinates the square of the distance di of the point mass mi from the z-axis is given by the sum of the squares of the x and y coordinates of the point mass mi. The unit of the moment of inertia I is the unit of mass times the square of the unit of length, that is kilogram times meter squared in SI units. By virtue of this definition, the z component of the angular momentum L of the rotating body can be written as the product of the moment of inertia of the body with respect to the z-axis, and the z component of the angular velocity vector omega. We note that if the mechanical system consists of more bodies rotating about the z-axis with the angular velocities omega sub 1z, omega sub 2z and so on, and the moments of inertia of the bodies are I1, I2 and so on with respect to the axis of rotation, then the z component of the angular momentum L of the whole system is given by I1 times omega sub 1z, plus I2 times omega sub 2z and so on. Let us consider some experiments and examples illustrating the concept of moment of inertia of rotating bodies. In the first experiment we use a toy train on a track mounted on a bicycle wheel free to rotate about its fixed vertical axis, where the train and the wheel are initially at rest. By turning the power on, the train can be set in motion while the wheel starts to rotate in the opposite direction. If friction is neglected, the external forces acting on the system formed by the toy train with its track and the wheel do not produce torque with respect to the axis of rotation of the wheel pointing in the direction of the z-axis. That is, the z component of the torque produced by the external forces vanishes. Then the law of conservation of momentum tells us that the z component of the angular momentum L of the system is constant, and it must be zero if it was zero initially at rest. Let I1 denote the moment of inertia of the toy train with respect to the z-axis, and omega sub 1z denote the z component of the angular velocity vector of the moving train with respect to the lab frame. Similarly, let I2 and omega sub 2z denote the corresponding quantities for the wheel. We can write that the moment of inertia I1 times the angular velocity omega sub 1z, plus the moment of inertia I2 times the angular velocity omega sub 2z vanishes. Here the z component of the angular velocities omega 1 and omega 2 have opposite signs since they describe rotations in opposite directions. Then the absolute value of the ratio of omega sub 1z to omega sub 2z is equal to the ratio of I2 to I1. In other words, the ratio of the angular velocities of the train and the wheel is inversely proportional to the ratio of their moment of inertia. For a given angular velocity of the train, the angular velocity of the wheel is proportional to the moment of inertia of the train but inversely proportional to the moment of inertia of the wheel. In another experiment demonstrating the law of conservation of angular momentum, a student is sitting at rest on a revolving stool while she holds a pair of weights in her folded arms. The stool is set in motion by another person and we assume that the angular velocity omega of the system formed by the student with the weights and the stool is approximately constant. However, if she suddenly outstretches her arms with the weights, the angular velocity of the system will decrease. We interpret the result of the experiment in terms of the torque produced by the external forces acting on the system. By neglecting friction, we can assume that the component of the torque parallel with the axis of rotation vanishes, that is, the moment of inertia I of the system times its angular velocity omega is constant. When the student extends her arms holding the weights, she increases the total moment of inertia of the system, resulting in the decrease of the angular velocity of the rotation. By pulling her arms close to her body again, she reduces the moment of inertia I, which speeds the rotation of the system up to its initial angular velocity. Another demonstration of the conservation of angular momentum in the system is when the student sitting on the revolving stool holds a bicycle wheel with its axis pointing in vertical direction. If the student starts to spin the wheel, then she and the revolving stool are also set in motion and rotate in the opposite direction. If the student stops the spinning wheel, then the stool stops rotating as well. The interpretation of the result of the experiment is the same as in the previous demonstration, that is, the change in the moment of inertia of the whole system forces to revolve the stool or to stop the revolving stool due to the conservation of the angular momentum of the system. Now let us suppose that the wheel is spinning and the stool with the student is revolving with a constant angular velocity as seen in the image. If the student tilts the wheel such that the angle between its axis of rotation and the vertical direction is 45 degrees, then the stool will slow down and revolve with a lower angular velocity. If the axis of rotation of the wheel becomes horizontal, then the stool will even not revolve at all. From both the demonstrations we can conclude that the angular momentum vector L of the wheel spinning about its axis of symmetry is given by the product of the moment of inertia I of the wheel and the angular velocity vector omega, and only the vertical component of the angular moment L has an effect on the rotation of the stool. A further demonstration can be made in the experiment with the revolving stool and the spinning wheel. If the student sitting on the stool at rest takes the wheel spinning about the vertical axis into her hands, then the stool remains at rest. However, if she flips the spinning wheel upside down such that he will spins in the opposite direction, then the stool starts to revolve. If the student turns back the wheel into its original position, then the stool stops revolving. The interpretation of the results is the following. When the student takes the spinning wheel in her hands, the system formed by the student, the stool, and the wheel gains the z component of the angular momentum L of the wheel, which is positive. This amount of angular momentum must be conserved since the z component of the torque tau of the system vanishes. However, when the spinning wheel is turned upside down, its angular momentum changes from plus L to minus L, that is, the change in it is equal to minus 2 times L. The law of conservation of angular momentum causes for the student with the stool to start to revolve so that they can gain the angular momentum of 2 times L, which holds the total angular momentum Lz of the system constant. The student sitting on the revolving stool at rest can also rotate the stool by applying internal forces. For example, if she raises one of the weights in her hands over her head and circle with the weight, then the stool starts to revolve in the direction opposite to the direction of the motion of the weight along its circular path. The revolving stool can even be rotated by a given angle without using the weight if the student repeats the following sequence of motion with one of her arms. She spreads out one arm forward and moves her outstretched arm behind her back in the horizontal plane, then folds it. Falling cats released from rest upside down produce similar motion. They can rotate about their horizontal axis through 180 degrees by using their legs or tail and land on their feet. An athlete swinging around a horizontal bar can increase his angular velocity at the proper moment, if he decreases the moment of inertia of his body with respect to the axis of rotation by compressing his body towards the bar. An interesting example is the possible variation in the angular velocity omega of the rotating Earth based on the situation illustrated in the second experiment, where the product of the moment of inertia I and the angular velocity omega is constant for a closed system. The variation in the speed of Earth's rotation might be due to some change in the moment of inertia of the planet. However, such a change must be cataclysmic in order to produce a non-negligible modification in the velocity of the rotation of Earth. Following the example described in the first experiment, the angular velocity of Earth could also be changed if millions of vehicles simultaneously traveled in the directions parallel with the equator from west to east, that is, in the direction of the rotation of the Earth. Although the solar system is generally considered as an open system exchanging energy and matter with its environment, it can be approximated as a closed system in many calculations related to celestial mechanics. Therefore, the magnitude and the direction of the angular momentum L of the solar system is constant. The plane perpendicular to the total angular momentum L and passing through the barycenter of the solar system is called the invariable plane of the system. The normal of this plane has a constant direction with respect to any inertial frame of reference, and in turn the invariable plane can be chosen as one of the coordinate plane of the inertial frames in astrometry. Our last example is the Segner wheel consisting of a vertical cylinder and one or two pairs of bent pipes with nozzles attached to the bottom of the cylinder. If the cylinder is filled with water, then the fluid is ejected from the nozzles due to the hydrostatic pressure, which produces torque on the wheel causing its rotation. In a Segner turbine, the working substance is normally steam, and the torque produced in such a system can be transmitted to a working device through a mechanism using belts and pulleys. The rotating motion produced by such wheels or turbines can be described by applying the law of conservation of angular momentum in a way similar to the one presented for the principle of propulsion. After having generalized the law of conservation of momentum and presented the law of conversion of angular momentum for a system of point masses, we will introduce the law of conservation of energy by generalizing the work-energy theorem for a system of point masses. We already saw that the work-energy theorem proved for a point mass states that the change in the kinetic energy E of the point mass is equal to the work W done by the force acting on the point mass. This theorem can also be formulated in a differential form stating that an infinitesimal change in the kinetic energy E of the point mass is equal to the infinitesimal work dW done by the force acting on the point mass. Now we prove the infinitesimal form of the theorem for a system of point masses m1, m2, ellipsis, mn with the instantaneous velocities v1, v2, ellipsis, vn where the forces f bar 1, f bar 2, ellipsis, f bar n are exerted on the point masses in the system. The equations of motion of the system of point masses state that the derivative of the momentum pi of the point mass mi with respect to the time t, or the mass mi times the time derivative of the velocity vi is equal to the net force f bar I acting on the point mass from I equals 1 to n. We can write the infinitesimal displacement vector dsi of the point mass mi as the product of the instantaneous velocity vi of the point mass and the differential of the time t. If we take the scalar product of the equations of motion and the infinitesimal displacement vectors dsi, and add them up, then we obtain the equation stating that the sum of the mass mi, times the dot product of the velocity vi and the differential of the velocity vi from I equals 1 to n, is equal to the sum of the dot product of the force f bar I and the infinitesimal displacement dsi from I equals 1 to n. Since the dot product of the velocity vi and its differential in the left-hand side of the equation is equal to 1 over 2 times the differential of the square of the velocity, we obtain the following expression. The differential of 1 over 2 times the sum of the mass mi times the square of the velocity vi from I equals 1 to n is given by the sum of the dot product of the force F bar I and the infinitesimal displacement ds from I equals 1 to n. In the right-hand side of the equation, the dot product of the force F bar I and the displacement vector dsi gives the infinitesimal work dwi done on the point mass mi by the force along the infinitesimal displacement. We already saw that the forces F bar I acting on a system of point masses include both internal forces acting between the particles of the system and the external forces applied on the system. Then we can split the infinitesimal work done on a given particle into some of the infinitesimal works done by internal and external forces. Considering the expression in the parentheses in the left-hand side of the equation, we define the kinetic energy E of a system of point masses m1, m2, ellipsis, mn with the instantaneous velocities v1, v2, ellipsis, vn, by the sum of the kinetic energies EI of the individual particles in the system, that is 1 over 2 times the sum of the mass mi times the square of the velocity vi from I equals 1 to n. Similarly, we can define the total infinitesimal work dw done on the whole system of point masses by the sum of the infinitesimal works dwi done on the individual point masses mi, that is the sum of the infinitesimal works done by the internal and external forces acting on the system. If we substitute these definitions into the original equation, then we can formulate the differential form of the work-energy theorem for a system of point masses, or in general for any mechanical system, stating that a change in the kinetic energy of a mechanical system is equal to the work done by the forces acting on the system. By integrating the differential form of the theorem, we can rewrite it for a finite change in energy produced by a finite amount of work as well. The equations of the energy-work balance show that both internal and external forces appear in the theorem, as opposed to the laws of conservation of momentum and angular momentum where only external forces have a role. The energy of a system of point masses can also be divided into two parts as we will show now. For a given system of point masses, we already define the center of mass or C of the system with respect to a reference point O by the sum of the mass mi times the position vector Ri of the point mass mi relative to the point O from I equals 1 to n over the total mass m of the system. The later is simply given by the sum of the masses mi of the particles in the system from I equals 1 to n. The velocity vc of the center of mass was obtained from the time derivative of the definition of the position vector of the center of mass, and it is equal to the sum of the mass mi times the velocity vi of the point mass mi over the total mass m of the system. Here the velocities are measured in the frame of reference which the reference point O is attached to. Then the position vector Ri of the point mass mi can be written as the vector sum of the position vector or C of the center of mass, and the vector R' pointing from the center of mass to the point mass mi, as shown for the point mass m1 in the figure. Similarly, the velocity vi of the point mass is equal to the vector sum of the velocity vc of the center of mass in the inertial frame which the reference point is attached to, and the velocity v'I of the point mass with respect to the frame of reference of the moving center of mass. Now the kinetic energy E of the system of point mass is given by 1 over 2 times the sum of the mass mi times the square of the velocity vi from I equals 1 to n, can be written as 1 over 2 times the sum of the mass mi times the square of the vector sum of vc and v'I. By expanding the bracket, we obtain 1 over 2 times the sum of mi from I equals 1 to n times vc squared, plus 1 over 2 times the sum of mi times v'I squared from I equals 1 to n, plus the dot product of vc and the sum of mi times v'I from I equals 1 to n. If we look at the expression of the velocity of the center of mass, then we recognize that the sum of mi times v'I is equal to the total mass m of the system times the velocity v'C of the center of mass in the frame of reference of the center of mass, which is of course 0. As a result, the last term vanishes in the right-hand side of the equation, leaving only the first two terms in the expression of the kinetic energy, that is 1 over 2 times the total mass m of the system times the square of the velocity vc of the center of mass, and 1 over 2 times the sum of mi times the square of v'I from I equals 1 to n. Then we can conclude that the kinetic energy of a system of point masses is the combination of the kinetic energy of the total mass of the system concentrated at the center of mass, and the kinetic energy of the system determined in the frame of reference of the center of mass. In order to illustrate this statement, we can consider the exploding grenade thrown in the air, which we already used as an example to study the motion of the center of mass of a mechanical system. We saw that the center of mass of the system moves along the same parabola in vacuum as the grenade before its explosion, since the internal forces causing the explosion have no effect on the motion of the center of mass. Then the kinetic energy of the grenade before explosion is given by the first term describing the motion of the center of mass. After the explosion, its kinetic energy will be increased with the second term describing the motion of the fragments, and this increment in energy is caused by internal forces. In the case of a rigid system of point masses, the work done by the internal and external forces acting on the system includes the work done by internal and external constraint forces. However, the work done by constraint forces vanishes in many cases, as we have already seen. In fact, it can be shown that the work done by constraint forces vanishes if the constraints imposed on the system are independent of time. For example, such a time-independent constraint is the several time aforementioned condition of the fixed distance between two arbitrary points of a rigid body, which states that the sum of the square of the differences between the corresponding Cartesian coordinates is constant during the motion of the body. Now we apply the work-energy theorem for conservative systems, which we will introduce below. If a system of point masses is a free system or the constraints imposed on the system are independent of time, then the work producing the change in the kinetic energy of the system in the work-energy theorem is the work done by all the free forces acting on the system. This work generally depends on the path along which it is done, where this path is represented by the individual trajectories of the particles in the system between their initial and final positions. Nevertheless, in many cases the free forces acting on the system are such that the work done by them does not depend on the path along which it is done. Furthermore, the mathematical expressions of these forces do not have an explicit dependence on time. We already considered such forces called conservative forces when we studied the law of conservation of mechanical energy for a point mass, stating that the sum of the kinetic energy and the potential energy, that is the mechanical energy of a point mass, is constant under the influence of a conservative force. As a result, we also saw that the work done on a point mass by a conservative force is equal to the decrease in the potential energy of the point mass. We call a mechanical system a conservative system if the free forces acting on the system are conservative forces. The case of conservative forces acting on point masses can be generalized to conservative mechanical systems. If in the initial state A of a system of point masses the particles have the positions R sub A1, R sub A2, ellipsis, R sub AN, and in the final state B the point masses have the positions R sub B1, R sub B2, ellipsis, R sub Bn, then the potential energy E of the system in the states A and B depends on these initial and final positions. Because the potential energy depends on the positions of particles in the system, each point mass has its own contribution to the potential energy of the whole system. The internal part of the potential energy is given by the interaction potentials between the particles in the system, assuming that the interactions are conveyed by conservative forces, whereas the external part is determined by the potential energy of each point mass in the presence of an external conservative field. If the conservative system evolves from the initial state A to the final state B, then the work W done by all the free forces is equal to the decrease in the potential energy E of the system depending only the states A and B. For differential displacements in the positions of the point masses, the infinitesimal amount of work dW done by all the free forces is equal to minus the differential of the potential energy E of the system. Now we are ready to formulate the law of conservation of energy for conservative mechanical systems. When we considered the evolution of such a system from its initial state A to its final state B, we were able to express the work W done along any path between the initial and final states as minus the difference between the potential energies in the states B and A. By applying the work-energy theorem, that is expressing the work W as the difference between the kinetic energies in the states B and A, we obtain the equation stating that the sum of the kinetic energy and the potential energy in the state A is equal to the sum of the kinetic energy and the potential energy in the state B. That is, the mechanical energy of the conservative system in its initial state is equal to the mechanical energy of the system in its final state. This is the law of conservation of mechanical energy for mechanical systems, telling us that in a conservative system the sum of the kinetic energy and the potential energy, that is the mechanical energy of the system, is constant if any constraint imposed on the system is independent of time. Due to the decomposition of the total work into the sum of the work done by internal forces and the work done by external forces, the potential energy of a conservative system is the combination of the internal and external potential energies. It is possible for a non-conservative system that its internal forces are conservative ones but the external forces acting on it are not. In this case we can talk about the internal potential energy of the system, but no external potential energy exists for such a system. The balance equation stating that the differential of the kinetic energy is equal to the infinitesimal amount of work done on the system given by the sum of the infinitesimal works done the internal and external forces still holds. But only the infinitesimal amount work done by the internal forces can be expressed as the negative differential of the internal potential energy of the system. As a result, the balance equation tells us that the sum of the differential of the kinetic energy and the differential of the internal potential energy of the system is equal to the infinitesimal amount of work done on the system by the external forces. Instead of the differential form of this equation, we can also use it with finite changes, stating that the sum of the change in the kinetic energy and the change in the internal potential energy of the system is equal to the work done on the system by external forces. After having presented the laws of conservation of momentum and energy for mechanical systems, we apply them to study the collision of bodies. Because collision is generally a complex phenomenon, we will only consider the collision of uniform spheres performing translation, which can be studied on balls suspended from long strings to provide quantitative results in experiments. For qualitative demonstrations, we can study the collision of balls rolling in grooves or button soccer, in which coin-shaped discs representing the players are flicked around a tabletop depicting a soccer pitch. We can also perform experiments only with coins hitting each other on a tabletop. There are several ways to classify the different types of collisions, depending on the relative positions of the centers of mass of the colliding bodies, the direction of the motion of the bodies at the moment of collision, or the nature of the transfer of the kinetic energy between the colliding bodies. Before presenting the classifications, we define the line of impact as the common normal to the contact surfaces at the point of contact between the colliding bodies. In the figure, the plane of contact describes the contact surfaces of the colliding spheres in the close vicinity of the point of contact, and the common normal is the normal to the plane of contact. If the centers of mass of the colliding bodies are located on the line of impact, then the impact is a central impact, and we talk about the central collision of the two bodies. If the center of mass of any one of the colliding bodies are not on the line of impact, then we have an eccentric impact, and we call their collision eccentric collision. Two spheres can only have eccentric collision if the center of mass of any or both of the spheres is not in the center of the given sphere, that is, the distribution of the density in the body is not spherically symmetric. An eccentric collision is only possible between bodies of uniform densities if at least one of them has a non-spherical shape, as seen in the figure. Another classification of collisions related to the directions of the motion of the colliding bodies. If the vectors representing the velocities of the colliding bodies are directed along the line of impact, the collision is called head-on collision. In other words, two bodies are moving directly towards each other and collide. If the velocity vector of one or both of the bodies is not along the line of impact, then we talk about oblique collision. In other words, the bodies are moving at an angle to each other and collide. Therefore, the collision of two uniform spheres is always central collision, but it can be either head-on or oblique, depending on whether the velocity vectors of the spheres with their tails at the center of mass lie on the same line or not. These two types of classification of collision are related to the geometric properties of the colliding bodies together with their kinematic initial conditions. The third type of classification, based on the nature of the energy transfer between the colliding bodies, needs more insight into the process of collision. The time of collision is normally very short, and its duration and the forces exerted in the collision during this time cannot be determined without a complicated measurement process. In order to avoid the difficulties related to such measurements, we will ignore the details of the process of collisions, and focus only the states of the colliding bodies before and after collision. We observe two spheres of masses m1 and m2 approaching each other with the velocities v1 and v2, let collide them, and determine their velocities v1' and v2' after the collision. Here the initial data is given by the velocities v1 and v2, where the impact can be central head-on or central oblique. We only give a brief explanation on what is happening during the short time of collision to interpret the energy exchange in the system formed by the colliding spheres, but we do not go into further details. The aim is to calculate the velocities v1' and v2' of the spheres after the collision based on the initial data and the masses of the colliding bodies, and examine their values related to the energy exchange. As external forces acting on bodies during their collision are generally negligible compared to the internal forces arising in the colliding bodies, we can treat the pair of these bodies as a closed system. In general, we can approximate any collision of bodies as a process in a closed mechanical system for which the law of conservation of momentum holds. That is, the total momentum of the spheres before the collision is equal to their total momentum after the collision, or the mass m1 times the velocity v1, plus the mass m2 times the velocity v2, is given by the mass m1 times the velocity v1', plus the mass m2 times the velocity v2'. We need to take into account that in the first half of the collision process the spheres start to deform and change their shapes till the component of their relative velocities in the direction of the line of impact becomes zero. Such a deformation can be illustrated by colliding laboratory carts with springs attached to their front, where at the collision of the cart some amount of the kinetic energy of the system is converted into the work related to the deformation of the compressed springs. Such conversion between kinetic energy and work producing the deformation happens to the colliding spheres as well. If in the second half of the collision process both the spheres return to their original shape and size, as in the case of the springs attached to the carts, and the system completely regains the amount of kinetic energy lost in the process of deformation, then we talk about the limiting case of an ideal collision and call it perfectly elastic collision. As a result, we can apply the law of conservation of energy in a perfectly elastic collision, stating that the kinetic energy of the system remains the same before and after the collision. The other limiting case of the collision is when the bodies stick together and the deformation caused by the collision is permanent, that is, the bodies cannot return to their original shape and size. We call this case perfectly inelastic collision, where the normal components of the velocities of the two bodies are equal after the collision. Here the work-energy theorem does not hold, since the work done producing the deformation cannot be converted back to kinetic energy. We start the study of the special cases of the collision of the two uniform spheres with perfectly elastic head-on collisions. As already seen, the law of conservation of momentum holds for any collision whether it is elastic collision or not, and it states that the mass m1 of the first sphere times its initial velocity v1, plus the mass m2 of the second sphere times its initial velocity v2, is equal to the mass m1 times the velocity v1 prime of the first sphere after the collision, plus the mass m2 times the velocity v2 prime of the second sphere after the collision. Because the collision is perfectly elastic, the total kinetic energy of the spheres does not change, that is, the law of conservation of energy also holds, which states that 1/2 times the mass m1 times the square of the velocity v1, plus 1/2 times the mass m2 times the square of the velocity v2, is equal to 1/2 times the mass m1 times the square of the velocity v1 prime, plus 1/2 times the mass m2 times the square of the velocity v2 prime. In the case of a head-on collision, all the velocity vectors lie on the line of impact, and we can direct the x-axis of a coordinate system along this line. Because the centers of mass of the spheres move along the x-axis, the vector equation written for the conservation of momentum can be reduced to a scalar equation with the x components of the velocity. However, the scalars v1 and v2 will not denote the magnitude of the vectors along the x-axis. They can be either positive or negative depending on the direction of the motion of the spheres. Any of the scalars will be positive if the corresponding sphere moves in the direction of the x-axis, and negative if it moves in the opposite direction. Then the equation obtained from the law of conservation of momentum states that the mass m1 times the difference between the velocity v1 prime and the velocity v1, is equal to the mass m2 times the difference between the velocity v2 and the velocity v2 prime. Similarly, the law of conservation of energy gives the equation stating that the mass m1 times the difference between the square of the velocity v1 prime and the square of the velocity v1, is equal to the mass m2 times the difference between the square of the velocity v2 and the square of the velocity v2 prime. Here we can use the algebraic identity stating that a squared minus b squared is equal to the product of a plus b and a minus b. If we divide the last equation by the scalar equation derived from the law of conservation of momentum, then we obtain the equation stating that v1 plus v1 prime is equal to v2 plus v2 prime, or the difference between v1 prime and v2 prime is equal to the difference between v2 and v1. We can express the velocity v2 prime as v1 prime plus v1 minus v2, and substitute it into the first scalar equation. By moving v1 prime into the left-hand side of the equation and v1 into the right-hand side, we obtain an equation stating that the sum of m1 and m2 times v1 prime is equal to 2 times m2 times v1, plus the difference between m1 and m2 times v2. Then the velocities after a perfectly elastic head-on collision are the following. The velocity v1 prime is equal to the difference between the masses m1 and m2 over their sum, times the velocity v1, plus 2 times the mass m2 over the sum of the masses m1 and m2, times the velocity v2. Similarly, the velocity v2 prime is given by the difference between the masses m2 and m1 over their sum, times the velocity v2, plus 2 times the mass m1 over the sum of the masses m1 and m2, times the velocity v1. The later formula can be obtained by eliminating v1 prime instead of v2 prime from the law of conservation of momentum and solving the result for v2 prime. Now we examine some special cases based on the ratios of the masses and the initial velocities. If the masses of the two spheres are equal, then the velocity v1 prime is equal to the velocity v2 and the velocity v2 prime is equal to the velocity v1. That is, the colliding spheres exchange each other's velocities. For example, if the second sphere was at rest before the collision, that is v2 is equal to 0, then v1 prime vanishes and v2 prime is equal to v1, which means that the first sphere will stop and the second one is set in motion with the velocity of the first sphere. If the sphere of velocity v1 has a collision with a sphere of much greater mass at rest or with an elastic wall, then the velocity v1' is approximately equal to minus v1, and the velocity v2' is approximately equal to 0 or vanishes for the wall. This means that the first sphere will bounce off approximately with the same velocity while the second sphere essentially stays at rest. In the case of the collision with a perfectly elastic wall, the magnitude of the velocity is exactly the same before and after the collision. Now we consider perfectly inelastic head-on collisions which can approximately be achieved in the collision of plumb spheres or even of sandbags. In nature, a good example for such collisions is a meteorite striking Earth's surface. In such a situation, the equations obtained from the law of conservation of momentum still gives the same equation as in the case of the perfectly elastic case, that is the mass m1 times the velocity v1 plus the mass m2 times the velocity v2, is equal to the mass m1 times the velocity v1' plus the mass m2 times the velocity v2'. However, in the perfectly inelastic case, the kinetic energy of the system is not conserved and the velocity v1' is equal to the velocity v2'. From these two equations we conclude that the velocity v1' and the velocity v2' are equal to the sum of the mass m1 times the velocity v1 and the mass m2 times the velocity v2 over the sum of the masses m1 and m2. In the right-hand side of the equation we can recognize the velocity vc of the center of mass of the system formed by the two spheres. Evidently, the spheres stuck together represent a single body with the mass of the total mass of the spheres, and the velocity of every part of the system is described by the velocity of the center of mass of the system. If the masses of the spheres are equal and the second sphere was at rest before the collision, then the velocities of the spheres are equal to the initial velocity of the first sphere over 2. That is, the second sphere will gain the half of the initial velocity of the first one, as opposed to the corresponding case with the perfectly elastic collision where the second sphere gained the total velocity of the first one and the later stopped after the collision. As already seen, the permanent deformation of the bodies after collision causes the loss of some amount of kinetic energy stored in the system, and the kinetic energy of the system is reduced after the inelastic collision. The kinetic energy of the system before the collision is given by the sum of the kinetic energies of the individual spheres, that is 1 over 2 times the mass m1 times the square of the velocity v1, plus 1 over 2 times the mass m2 times the square of the velocity v2. The kinetic energy of the system after the collision is the kinetic energy of the spheres stuck together with the mass of m1 plus m2 and the velocity vc of the center of mass of the system. Here the formula describing the velocity of the center of mass is also inserted into the expression. Since the denominator of the fraction in the right-hand side is the sum of the masses m1 and m2, we will expand the fractions in the left-hand side by this sum. By simplifying the result, we obtain a fraction with the same denominator as the one seen in the right-hand side, where the square in the numerator can be expanded as well. Now we can determine the decrease in the kinetic energy of the system due to the collision by calculating the absolute value of the difference between the expressions derived on both sides. If we compare the numerators in the two sides, we immediately see that the terms with the m1 squared and m2 squared cancel out. Then the numerator of the difference reduces to m1 times m2 times v1 squared, plus m1 times m2 times v2 squared, minus 2 times m1 times m2 times v1 times v2. We can factor out the product of m1 and m2 from the three terms in the numerator, which gives 1 over 2 times the mass m1 times the mass m2 over the sum of m1 and m2, times the square of the difference between the velocities v2 and v1. This result shows that the reduction in the kinetic energy of the system is proportional to the square of the relative velocity of the colliding spheres with perfectly inelastic head-on impact. Because the ratio of the product of the mass m1 and the mass m2 divided by their sum is called the reduced mass of the system, we can say that the proportionality constant is the half of the reduced mass of the system. In the special case where the second sphere is initially at rest and its mass tends to infinity or it can be replaced with an inelastic wall, the reduced mass tends to the mass m1 and the decrease in the kinetic energy is equal to the kinetic energy of the sphere before the collision. In other words, the total kinetic energy is lost since it is completely converted into heat in the perfectly inelastic collision. After the discussion on colliding bodies with head-on impact, we examine perfectly elastic oblique collisions where two different cases will be considered. In the first case, the sphere of mass m1 traveling with the velocity v1 either collides with a sphere of mass m2 much greater than the mass m1 initially at rest, or with a wall, where the angle between the direction of the velocity v1 and the line of impact is denoted by alpha. In the figure we depicted both the massive sphere and the wall, where the surface of the wall defines the plane of contact for both the cases. The velocities v1 and v1' can be decomposed with respect to the plane of impact into normal and tangential components. We have seen in the similar example for perfectly elastic head-on collisions that the sphere of mass m1 bounces off the more massive sphere at rest or the wall with the same speed in the opposite direction. By applying this finding for the oblique case, we see that the component of the velocity v1 normal to the plane of impact changes its sign after the collision, whereas the tangential component of v1 does not change provided friction can be neglected. As a result, the magnitude of the velocity v1' of the sphere bouncing off does not change, where the scattering angle beta between the direction of the motion of the sphere after collision and the line of impact is equal to the angle alpha of the impact. In the second case, the sphere of mass m1 collides with a sphere of mass m2 at rest with an oblique impact indicated by the different directions of the common normal n to the surface of contact and the velocity v1 of the first sphere, where the spheres have the same masses, that is m1 is equal to m2. If we apply the laws of conservation of momentum and energy for this case with m1 equals m2 and v2 equals 0, their mathematical expressions can be reduced to the equation stating that the incoming velocity v1 of the first sphere is equal to the outgoing velocity v1' of the first sphere plus the outgoing velocity v2' of the second sphere, and the equation stating that the square of the velocity v1 is given by the square of the velocity v1' plus the square of the velocity v2'. The first equation tells us that the initial velocity v1 of the first sphere is equal to the vector sum of the velocities v1' and v2' of the spheres after the collision, whereas the second equation is the Pythagorean theorem formulated for the magnitudes of the velocities. Then we can conclude the following. Whatever the direction of the line of impact is, the outgoing velocities v1' and v2' of the spheres are always perpendicular to each other after an oblique collision. We have presented the basic examples of limiting cases for perfectly elastic and inelastic collisions. Real collisions are neither perfectly elastic collisions nor perfectly inelastic ones. We can examine the states of the spheres of masses m1 and m2 before and after a real collision. If we decompose the velocities v1 and v2 of the incoming spheres and the velocities v1' and v2' into the normal and tangential components with respect to the plane of contact. In the case of perfectly elastic collisions, the relative velocities or in more general their normal components have the same magnitudes before and after the collision, that is the difference between the normal component of v1 and the normal component of v2, is equal to the difference between the normal component of v1' and the normal component of v2'. In a real situation, the elastic forces producing the deformation of the spheres do not restore the original magnitude of the normal component of the relative velocities after the spheres return to their original shape and size. In other words, the difference between the normal component of v2 and the normal component of v1 is greater than the difference between the normal component of v1' and the normal component of v2'. The ratio of these differences defines the coefficient E of restitution, which is one of the characteristics of the material properties of the colliding bodies, and it is independent of their velocities at least in first order. By definition, this coefficient is between 0 and 1. The two limiting cases are the perfectly elastic collision where the coefficient of restitution is equal to 1, and the perfectly inelastic collision with the vanishing coefficient of restitution. The table shows the results obtained in the measurements of the coefficient of restitution for a pair of colliding spheres made of different materials. This coefficient, as a measure of the elasticity of the collision, shows that the collision of glass or ivory spheres is very elastic, whereas a pair of lead spheres mentioned as an example before has a rather inelastic collision. In the case of the real head-on collision of a sphere of mass m1 traveling with the velocity v1 and a sphere of mass m2 at rest, the law of conservation of momentum still holds, stating that the mass m1 times the velocity v1 is equal to the mass m1 times the velocity v1' plus the mass m2 times the velocity v2'. Because some amount of kinetic energy is converted to heat in a real collision, that is, the colliding spheres do not form a conservative system, the law of conservation of energy does not hold here. We can only apply the definition of the coefficient of restitution to express the difference between the velocities v2' and v1' after the collision, as E times the initial velocity v1. For head-on collisions, the velocities are parallel with the normal to the plane of contact, and we do not need to use the subscripts for the normal components. If we express the velocity v2' from this equation and substitute it into the law of conservation of momentum, we can solve the resulting equation for the outgoing velocity v1' of the sphere of mass m1. Then we can write it as the difference between the mass m1 and the coefficient of restitution E times the mass m2 of the second sphere over the sum of the masses m1 and m2, times the incoming velocity v1 of the first sphere. By inserting this expression into the definition of the coefficient of restitution, we can express the velocity v2' of the sphere initially at rest as 1 plus e times the mass m1 over the sum of the masses m1 and m2, times the velocity v1. Now we consider an example already seen in the discussion on the ideal limiting cases, where the mass m1 of the first sphere is negligible compared with the mass m2 of the second sphere, or we simply replace the second sphere with a wall described by the mass m2 that tends to infinity. As a result, the velocity v1' of the sphere bouncing off the more massive sphere or the wall, is equal to minus the coefficient of restitution e times the incoming velocity v1, whereas the velocity v2' still vanishes. Here the first formula tells us that the incoming velocity of the sphere is reduced by a factor that is the coefficient of restitution after the collision. We can apply this formula for a ball dropped from the height h1 hitting any horizontal surface to calculate the maximum height h2 that the ball can reach after bouncing back. In the study of free fall, we saw that the ball has the velocity v1 given by the square root of 2 times the magnitude of the gravitational acceleration g times the height h1 when it hits the horizontal surface. Then the velocity v1' of the ball bouncing back is equal to the coefficient of restitution times the velocity v1, and the ball bounces back to the height h2 given by the square of e times v1 over 2 times g. This gives e squared times h1. That is, the height to which the ball bounces back is e squared times shorter than the height from which the ball was dropped. After the ball bounced back n times, the maximum height will be the coefficient of restitution e to the power of 2n times shorter than the initial height h1 of the ball. We note that in all the cases presented here for collisions we assume that the colliding spheres perform translational motion. If the colliding bodies are also rolling, like the billiard balls on the table, then we also need to apply the law of conservation of angular momentum and take into account both the friction and the kinetic energy associated with rolling. In the last topic related to collisions we present a laboratory apparatus called ballistic pendulum which is used to demonstrate the conservation of momentum in inelastic collisions. Ballistic pendulum is a device for measuring the velocity or the momentum of a projectile such as a bullet, or more generally studying the effect of a force exerted on an object for a short time of the impact of the projectile. That is the impulse caused by the impact. The device was invented in 1742 by Benjamin Robbins, a British mathematician and military engineer, who introduced it to measure the velocity of a bullet with high accuracy in his studies of ballistics. A ballistic pendulum consists of a heavy wooden block suspended from a pivot, that is the wooden block serving as the bob of the pendulum. 2 long cords were usually applied for the suspension of the bob, but both the original and modern versions of the instrument use a firm and lightweight arm, as seen in the figure in the photo. If a projectile of mass m1 traveling with the velocity v1 in a horizontal direction strikes the wooden block of mass m2 and penetrates the bob, then the bob with the bullet swings back in an arc around the pivot. Then the horizontal and vertical distances of the wooden block at the turning point of the swing measured from its initial position are denoted by the length x1 and the height h respectively. The law of conservation of momentum can be applied for the inelastic collision of the projectile and the bob, stating that the mass m1 of the projectile times its velocity v1 is equal to the sum of the masses m1 and m2 times the velocity vc of the center of mass of the system formed by the two objects. By measuring the velocity vc of the bob after the collision we can determine the velocity v1 of the projectile moving much faster. Because the time tau of the collision is negligible compared with the period t of the swinging pendulum, the velocity vc can be considered as the initial velocity of the pendulum leaving its equilibrium position. Then the maximum height h attained by the bob is equal to the square of the initial velocity vc over 2 times the magnitude of the gravitational acceleration g, and we can express the velocity vc from this equation as the square root of 2 times g times h. If we solve the equation describing the conservation of momentum for the velocity v1 of the projectile, it gives the sum of the masses m1 and m2 over the mass m1, times the velocity vc. By substituting the formula for vc into the right-hand side, we can write the velocity v1 as 1 over the ratio of the mass m2 to the mass m1, times the square root of 2 times g times the maximum height h. This relation between v1 and h allows one to determine the velocity of the projectile from the maximum height h which the bob will rise to. With an appropriate length L of the pendulum and the mass m2 of the bob, the angular displacement phi of the bob can be reduced such that the small angle approximation can be applied for the swings of pendulum, where phi can be expressed as the ratio of the displacement x1 to the length L. When we studied mathematical pendulum in such an approximation, we saw that its motion in the horizontal direction can be described as a simple harmonic motion about the equilibrium position of the bob. The angular frequency omega of the harmonic motion of the bob given by 2 pi times over the period t is equal to the square root of the gravitational acceleration g over the length L, and the initial velocity vc of the wooden block can be written as the angular frequency omega times the displacement x1 of the bob for the first swing, or 2 pi times over the period t, times x1. Instead of measuring the height h, we can therefore perform a more accurate measurement of the period t of the swing and the maximum horizontal displacement x1 of the bob in order to determine the velocity of the projectile. Ballistic pendulum can also be used to measure the impulse caused by the impact of the projectile. In general, if a horizontal force F is applied on a pendulum of mass m for a time tau much shorter than the period t of the pendulum, then the impulse J defined by the integral of the force F over the time tau with respect to the time t is equal to the mass m times the velocity vc of the pendulum, that is the momentum gained by the bob under the influence of the force. In the case of the ballistic pendulum, the total mass m of the pendulum is just the sum of the mass m1 of the projectile and the mass m2 of the bob. By inserting the expression obtained for the velocity from the approximation using simple harmonic motion, we can write the right-hand side as the mass m times the angular frequency omega, times the maximum horizontal displacement x1 for the first swing of the bob. As we can see, the impulse J is directly proportional to the maximum displacement x1, where the proportionality constant is equal to the mass m of the pendulum times the angular frequency omega for the first swing of the bob. This proportionality constant describing the impulse per unit displacement can be interpreted as the sensitivity of the ballistic pendulum in the measurement of the impulse transferred by the force F. Ballistic pendulums can be used to measure the force F as well. In the case of the small angle approximation for the swing of the bob, we can assume that Hooke's law holds, stating that the horizontal restoring force F driving the bob back to its equilibrium position is equal to minus k times the displacement x of the bob. The constant k for the pendulum can be written as the mass m of the bob times the gravitational acceleration g over the length L of the pendulum, where the ratio of g to L is equal to the square of the angular velocity omega. If the constant force F now represents the impact of the projectile on the bob producing a given displacement x governed by Hooke's law, then this force can be written as the constant k times the displacement x of the pendulum. Because the constant k is equal to the mass m times the square of the angular velocity omega, it is also given by m times the ratio of 4 pi squared to the square of the period t. Here k or m times omega squared describing the force per unit displacement can be interpreted as the sensitivity of the ballistic pendulum in the measurement of the force F. By comparing it with the sensitivity of the measurement of impulse, we see that the sensitivity of measurement of force is given by the angular velocity omega times the sensitivity of the measurement of impulse. As an example, let us suppose that the length L of the pendulum is equal to 1 meter and its bob has a mass of 1 kilogram. Then the period t of the pendulum is given by about 2 seconds. As a result, the constant k is equal to 10 Newton per second and the sensitivity given by m times omega is equal to 3.2 Newton second per meter. For a projectile striking the bob and producing the maximum displacement x1 of 0.1 meter of the pendulum, the impulse J is equal to 0.32 Newton second, whereas the velocity of the projectile is given by 0.32 meter per second. We finished the discussion on the mechanics of systems of point masses with the Virial theorem proven for such systems. In order to introduce the quantity called Virial playing the basic role in this theorem, we need to generalize the concept of moment of inertia of a system of point masses about an axis to the moment of inertia about a point. Let us consider a system of point masses m1, m2, ellipsis, mn, and denote the position vector of the point mass mi with respect to a reference point O by Ri from I equals 1 to n. Let also Vi denote the velocity of the point mass mi, where the momentum Pi of the point mass is given by the product of its mass mi and its velocity Vi. The net force Fi acting on the point mass mi is equal to the vector sum of all the forces exerted on the point mass. For such a mechanical system, we can define the moment of inertia I about the point O by the sum of the product of the mass mi and the square of the magnitude of the position vector Ri from I equals 1 to n. Here the square of the magnitude of the position vector Ri is simply given by the dot product of the vector with itself. We note that the definition of I can be expressed as a function of the distances between the point masses of the system, if we determine the sum of the mass mi times the mass mj times the dot product of the difference between the position vectors Ri and Rj from I and j equal 1 to n. Because the dot product can be written as Ri squared minus 2 times the dot product of Ri and Rj plus Rj squared, we can express the right-hand side as 3 terms containing double sums. The first term is given by the sum of mj from j equals 1 to n, times the sum of mi times Ri squared from I equals 1 to n, whereas the second term is equal to minus 2 times the dot product of two sums. The sum of mi times ri squared from I equals 1 to n, and the sum of mj times rj squared from j equals 1 to n. The last term is given by the sum of mi from I equals 1 to n, times the sum of mj times rj squared from j equals t to n. Both the sums of the masses mi and mj in the first and the last terms give the total mass m of the system, whereas both the sums of the products of mi and ri squared and the products of mj and rj squared are equal to the moment of inertia I of the system. Then we have 2 times the total mass m of the system times its moment of inertia I. In the dot product in the second term can recognize the mass m times the center of mass or c of the system, that is we have minus 2 times m squared times or c squared. Since the left-hand side is symmetric the indices I and j, we can express the moment of inertia I from this equation as 1 over the total mass m times the sum of the mass mi times the mass mj times the square of the distance r sub ij between the point masses mi and mj from I equal 1 to n and j less than I, plus the total mass m times the square of the center of mass or c. This form of the moment of inertia is more useful for the study of the time evolution of the distances between the point masses in a system. Now we use the original form of the definition of the moment of inertia to calculate the rate of its change. For the sake of convenience we determine 1 over 2 times the derivative of I with respect to the time t. Then we obtain the sum of mi times the dot product of the time derivative of ri and ri from I equals 1 to n. Here ri dot is simply the velocity vi of the point mass mi, and mi times vi is defined as the momentum pi of the point mass. As a result, the second-order derivative of the moment of inertia I with respect to the time t can be written as the sum of the dot product of the derivative of the momentum pi and the position vector ri from I equals 1 to n, plus the sum of the dot product of pi and the derivative of ri. The derivative of ri in the second term can also be written as vi. For the first term in the right-hand side we can apply the equations of motion of the system stating that the time derivative of the momentum pi of the point mass mi is equal to the net force Fi acting on the point mass where the index I is running from 1 to n. If we insert these equations into the second-order time derivative of the moment of inertia I, then the first sum becomes the dot product of the force Fi and the position vector ri, whereas the second sum can be written as the mass mi times the dot product of the velocity vi with itself. In the second sum the dot product gives the square of the velocity vi, where we can identify the total kinetic energy of the system defined as the sum of the kinetic energies of the individual point masses, that is 1 over 2 times the sum of the mass mi times the square of the velocity vi from I equals 1 to n. Now we substitute the definition of the total kinetic energy of the system into the equation describing half the second-order time derivative of the moment of inertia, which we can also call the acceleration of the inertia I, and write it as the sum of the dot product of the force Fi acting on the point mass mi and the position vector ri of the point mass from I equals 1 to n, plus 2 times the total kinetic energy of the system. In the 19th century when Rudolf Clausius, a German theoretical physicist, formulated and proved the Virial theorem, it was a common practice to assign a Latin name to any special characteristic of a physical system. At that time kinetic energy was often called vis viva, meaning living force, and Clausius also coined the term virial stemming from the plural form virias of the word vis, that is force. He called half the first term in the right-hand side virial, that is the half the sum of the dot product of the force Fi and the position vector ri from I equals 1 to n represented a special property of the system of point masses for Clausius. This quantity summing up the projections of the forces acting on the point masses onto the position vectors of the point masses measures the bound due to the interactions between the particle, where the forces include the forces of interactions. Then the equation in the left-hand side states that half the acceleration of the moment of inertia of a system of point masses is given by the sum of 2 times the virial representing the forces acting on the system and 2 times the kinetic energy of the system. If all the forces Fi acting on the point masses mi are conservative forces, that is the system of point masses is a conservative system, then we can define the potential energy of the system as a function of the position vectors ri of the point masses for the index I running from 1 to n. Each conservative force Fi acting on a point mass mi is given by the negative gradient of the potential energy of the system, where the gradients are always calculated with respect to the components of the position vector ri of the point mass. For example, if we attach the origin of a Cartesian coordinate system to the reference point O, then the Cartesian coordinates of the position vector ri can be written as xi, yi and zi. Similarly, the Cartesian components of the force Fi denoted by f sub ix, f sub iy, and f sub iz are equal to the negative partial derivative of the potential energy with respect to the corresponding coordinate of the position vector ri. Then the sum in the virial can be written as the sum of f sub ix times xi, plus f sub iy times yi, plus f sub iz times zi from I equals 1 to n, or minus the sum of three terms, xi times the partial derivative of the potential energy with respect to xi, plus yi times the partial derivative of the potential energy with respect to yi, plus zi times the partial derivative of the potential energy with respect to zi, from I equals 1 to n. Because the terms in the parentheses give the projection of the gradients into the direction of the position vectors of the point masses, half the virial is equal to the sum of the directional derivatives of the potential energy of the system along the position vectors for all particles in the system. As a result, 1 over 2 times the second-order time derivative of the moment of inertia I of a system of point masses under the influence of conservative forces is given by 2 times the total kinetic energy of the system, minus the sum of the directional derivatives of the potential energy of the system along the position vectors I from I equals 1 to n. In many cases the potential energy of a mechanical system under the influence of conservative forces is a homogeneous function in its variables, normally some coordinates describing the configuration of the system. Then Euler's theorem for homogeneous functions can be applied in calculating the gradient of the homogeneous potential energy of the system, which allows us to simplify the virial in the second-order differential equation of the moment of inertia of the conservative system. We call a function f of n variables a homogeneous function of degree k in its first variables x1, x2, ellipsis, xm with m less than or equal to n, if the function f evaluated at lambda times x1, ellipsis, lambda times xm, xm plus 1, ellipsis, xn, is equal to lambda to k times the function f evaluated at x1, ellipsis, xm, xm plus 1, ellipsis, xn. Here lambda is an arbitrary real parameter. First we compute the derivative of this equation with respect to the parameter lambda. By introducing the notation y for lambda times xi, we can write the derivative of the left-hand side as the derivative of the function f evaluated at y1, ellipsis, ym, xm plus 1, ellipsis, xn with respect to lambda, and apply the chain rule for the function yi. Then we obtain the sum of the partial derivative of the function f with respect to yi at constant yj where j is not equal to I, times the partial derivative of yi with respect to lambda, from I equals to 1 to m. If we substitute the definition of yi into the derivatives, then we take the partial derivatives of the function f with respect to lambda times xi, and the derivative of yi with respect to lambda can be written as xi. Now we compute the derivative of the left-hand side of the definition of the homogeneous function f. The derivative of lambda to k times the function f with respect to lambda, is equal to k times lambda to k minus 1, times the function f. By inserting these two equations into the derivative of the definition of the homogeneous function f and setting the arbitrary parameter lambda to 1, we obtain Euler's theorem for homogeneous functions, which states the following. If a function f of n variables is a homogeneous function of degree k in its first m variables, then k times the function f is equal to the sum of the derivative of the function f with respect to xi, times xi from I equals to 1 to m. If we suppose that the potential energy of a conservative system depends on n position vectors and it is a homogeneous function of degree k in its all variables, then we can state that the potential energy of the system evaluated at the position vectors I scaled by the factor lambda, is equal to lambda to k times the potential energy evaluated at the positions I from I equals 1 to n. By applying Euler's theorem for such a homogeneous potential energy, we can write the sum of its directional derivative along the position vectors from I equals 1 to n, as k times the potential energy itself. As a result, half the acceleration of the moment of inertia I of a conservative system with a homogeneous potential energy of degree k can be written as 2 times the kinetic energy of the system, minus k times the potential energy of the system. Now we will provide an example of a mechanical system that has a homogeneous potential energy as an illustration of Euler's theorem applied in the calculation of the virial. Let us suppose that a system of point masses is a closed system, that is, no external forces are applied on the particles in the system. Then the net forces acting on the point masses are the internal forces describing the interactions between the particles, and the force Fi acting on the point mass mi is the vector sum of the forces F sub ij exerted on the point mass mi by the point mass mj for I and j equal 1 to n, where the indices I and j are different. The later condition indicates that there is no self-interaction in particles, and the vector sum of these forces gives the net effect on the point mass mi by the rest of the point masses in the system. By substituting this vector sum into the force Fi in the virial of the system of point masses, we can write its sum as the sum of the dot product of the force F sub ij and the position vector I from I and j equal 1 to n, where I is not equal to j. Now we expand the double sum as follows. In the first row we write the terms with the index I equals 1 while expanding the sum with the index j. Because the index I must not be equal to the index j, we start with a vanishing term for I equals j where the force F sub 1 1 is equal to 0. Then we have F sub 1 2 times R1, plus F sub 1 3 times R1, plus ellipsis, plus F sub 1 n times R1. In the second row we write the terms with the index I equals 2, which are plus F sub 2 1 times R2, plus a vanishing term, plus F sub 2 3 times R2, plus ellipsis, plus F sub 2 n times R2. In the third row we can write the next terms, plus F sub 3 1 times R3, plus F sub 3 2 times R3, plus a vanishing term, plus ellipsis, plus F sub 3 n times R3. We can follow the same pattern till we reach the last row for I equals n, which has the terms plus F sub n 1 times Rn, plus F sub n 2 times Rn, plus ellipsis, plus F sub n n minus 1 times Rn, plus a vanishing term. Then we have n terms including one vanishing term in each row and all the terms are ordered in n rows. Because the terms of the sum are arranged in an n times n block, we have a matrix pattern where zeros can be found in the diagonal positions separating the areas of the lower and upper diagonals. Here we have collected the terms from the lower and upper diagonal positions of this sum separately into two groups arranged in two rows by applying the following strategy. We started with the first term in the second row belonging to the lower diagonal area, that is F sub 2 1 times R2 denoted by the yellow rectangles. Then we collected the terms in the third row belonging to the lower diagonal area into one sum denoted by the orange rectangle. We followed the same procedure till the last row where we collected the terms belonging to the lower diagonal area into one sum denoted by the red rectangle. We collected the terms in the upper diagonal area in a similar way. We started with the second term in the first row belonging to the upper diagonal area, that is F sub 1 2 times R1 denoted by the green rectangles. Then we collected the third column of the terms belonging to the upper diagonal into one sum denoted by the blue rectangle. We followed the same procedure till the last column of terms where we collected the dot products into one sum denoted by the purple rectangle. By collecting the terms from the lower and the upper diagonal areas and the sum of the virial we have obtained a set of sums arranged in two rows, which can be combined into two double sums. Then the sum in the virial of the system of point masses is given by the sum of the dot product of the force F sub ij and the position vector Ri from I equals 1 to n and for j less than I, plus the sum of the dot product of the force F sub ji and the position vector Rj from I equals 1 to n with the indices j greater than I. Here we can apply the third law of motion stating that the action F sub ij is equal and opposite to the reaction F sub ji for all the indices I and j running from 1 to n. If we substitute this law into the second sum in the right-hand side, then the sum in the virial of a system of point masses free from external forces reduces to the sum of the dot product of the force F sub ij and the difference between the position vectors Ri and Rj from I equals 1 to n and for j less than I. Because the difference between the position vectors of the point masses mi and mj gives the vector pointing from the point mass mj to the point mass mi, the dot products in the sum can be interpreted as the work done by the force Fij on the point mass mi over the distance connecting the two point masses. This means that the virial of a closed system of point masses is determined by the sum of the works done by the forces of interaction between the particles over the distances between them. After having expressed the virial of a closed system in terms of the interaction forces, we will assume that these forces are conservative, that is, they are independent of the velocities of the point masses and do not have explicit time dependence. In that case, we can define the total potential energy of the system of point masses as the sum of the potential energies of all the point masses in the system due to the interactions between the particles. Normally the potential energy of the interaction between the point masses mi and mj only depends on the distance between the point masses, that is the magnitude of the difference between the position vectors Ri and Rj. The force F sub ij describing the interaction between the point masses mi and mj is then given by the negative gradient of the interaction potential energy between the two particles with respect to the position vector Ri of the first point mass. Both of these relations will be applied when we determine the sum of the virial of a closed conservative system, which is expressed as the sum of the dot product of the interaction force F sub ij and the difference between the position vectors Ri and Rj from I equals 1 to j and for j less than I. First we insert the negative gradient of the potential energy of the interaction between two particles, and use the chain rule by writing the gradient of the potential energy depending only on the distance R sub ij as its derivative with respect to R sub ij, times the difference between Ri and Rj over R sub ij. Here we obtain the dot product of the difference between Ri and Rj, which gives the square of its magnitude. Because the later is just the square of the distance R sub ij between the point masses mi and mj, The sum in the virial can be written as minus the sum of the derivative of the potential energy of the interaction between the point masses mi and mj with respect to the distance r sub ij, times the distance r sub ij from I equals 1 to n and for j less than I. The potential energy of the interaction between the point masses mi and mj normally obeys some power law of the distance between the particles, that can be written some real constant alpha sub ij, times the distance r sub ij between the point masses to the power of k, where k is an integer. If the interaction between the system of point masses is described by Newton's law of gravitation, then the magnitude of the force F sub ij exerted on the point mass mi at the point ri by the point mass mj at the point rj, is given by minus the gravitational constant times the product of the masses mi and mj over the square of the distance r sub ij between the point masses. Its direction is determined by minus the unit vector ri minus rj over its length, which points from the point mass mi to the mj. Because gravitational forces are conservative, the potential energy of the gravitational interaction between the 2 point masses can be defined, and it must be equal to minus the gravitational constant g, times the product of the masses mi and mj over the distance between the point masses given by the magnitude of the difference between the position vectors ri and rj. Then the multiplication factor in the power law for gravity is given by minus g times mi times mj, and the exponent k is equal to minus 1. The derivative of the potential energy of any interaction between 2 point masses mi and mj described by the power law with respect to the distance rij between the point masses, is equal to k times alpha sub ij times r sub ij to k minus 1. If we substitute this result into the sum of the virial in the left-hand side, then we obtain minus k times the sum of alpha sub ij, times the distance r sub ij to k from I equals 1 to n and for j less than I, which is equal to minus k times the sum of the potential energies of the interactions between the point masses mi and mj from I equals 1 to n and for j less than I. Since the double sum gives the total potential energy of the interactions between all the point masses in the system, we conclude that the sum in the virial is equal to minus k times the potential energy of the system. This is an illustration of the fact that the potential energy of a conservative system with a power law interaction potential is a homogeneous function of degree k. Indeed, any scaling of the distance r sub ij in the power law by lambda can be factored out, producing a multiplication factor of lambda to k. We have already established that 1 over 2 times the second-order time derivative or the acceleration of the moment of inertia I of a conservative mechanical system where the potential energy is a homogeneous function of degree k in its variables, that is the coordinates describing the state of the system, is equal to 2 times the kinetic energy of the system, minus k times the potential energy of the system. As seen in the example of Newton's law of gravitation, the degree k is equal to minus 1 for a self-gravitating system of point masses, which gives Lagrange's identity stating that 1 over 2 times the second-order time derivative of the moment of inertia I, is equal to 2 times the kinetic energy of the system plus the potential energy of the system. This identity was introduced in the study on the three-body problem in 1772 by Joseph Louis Lagrange, an Italian-French mathematician and physicist, although he did not use the modern terminology of moment of inertia or energy. Besides Lagrange's identity, the law of conservation of energy also holds for a closed system, stating that the total energy E of the system given by the sum of its kinetic energy and its potential energy is constant. Then we can write that the constant total energy E minus the potential energy of the system is equal to its kinetic energy, which is always greater than or equal to 0 for a system of point masses due to the fact that its kinematic energy is a quadratic function of the velocities of the particles. The kinetic energy of the system only vanishes if all the point masses in the system stay at rest. If we insert this equation into Lagrange's identity, then we obtain the Lagrange-Jacobi formula stating that 1 over 2 times the second-order time derivative of the moment of inertia I, is equal to 2 times the total energy of the system minus the potential energy of the system. This formula was derived by Carl Gustav Jacob Jacobi, a German mathematician who generalized Lagrange's identity to the n-body problem. We have already seen that the potential energy for the gravitational interaction between particles is negative. It therefore follows from the law of conservation of energy that the total energy E of a self-gravitating system must be positive. As a result, the right-hand side of the Lagrange-Jacobi formula is positive, that is, the second-order time derivative of the moment of inertia I is positive. In other words, the rate of change of the moment of inertia is increasing, and it has a consequence related to the stability of the self-gravitating system. The Lagrange-Jacobi formula is a second-order differential equation with respect to the time, and we need to integrate it 2 times to solve it for the moment of inertia I. The first integration gives an equation stating that 1 over 2 times the derivative of the moment of inertia I is equal to the integral of the difference between 2 times the total energy E and the potential energy from 0 to the parameter T0 with respect to the variable T1, plus an integration constant denoted by I1. The second integration gives 1 over 2 times the moment of inertia I as a function of time expressed as the double integral of the difference between 2 times the total energy E and the potential energy, from 0 to T0 and from 0 to T with respect to T1 and T0, plus the integration constant I1 times the time T plus a second integration constant I0. Because the total energy E is constant for a closed system, it can be integrated 2 times, and 1 over 2 times the moment of inertia I can be expressed as the total energy E times the square of the time T, plus the integration constant I1 times the time T, plus the integration constant I0, minus the double integral of the potential energy of the system with respect to the time. We saw that the total energy is positive and the potential energy is negative in the case of a closed self-gravitating system of point masses. It can also be shown that the potential energy is bounded for such a system, and its double integral can be replaced by a constant representing the negative lower bound times the square of the time t. Then the moment of inertia I is the order of the square of the time t as the time t tends to infinity, that is the moment of inertia diverges with time. We can understand the consequence of its divergence if we look at the moment of inertia of a system of point masses expressed in terms of the distances between the particles in the system. We found that it is 1 over the total mass m of the system, times the sum of the mass mi times the mass mj times the square of the distance r sub ij between the particles from I equals 1 to n and for j less than I, plus the total mass m times the square of the center of mass or c of the system. When studying the law of conservation of momentum, we also saw that the center of mass of a closed mechanical system either performs a uniform motion in a straight line or remain at rest. If we attach the frame of reference to the center of mass by choosing Rc as the reference point O, then the second term in the right-hand side vanishes and the moment of inertia only depends on the instantaneous distances between the particles of given masses. If the moment of inertia for such a system diverges, this formula shows that at least one of point masses moves away from the rest of the particles and travels to infinity. After the introduction of the Lagrange-Jacobi formula, Jacobi developed the stability criterion for n-body systems based on this result in his lectures on dynamics delivered in 1842. His theorem states that if the total energy of a conservative system is positive, then at least one of the mutual distances between the point masses will increase to infinity as the time tends to infinity. In general, this theorem on the stability of the systems of gravitating bodies with non-negative energy states that some of the inter-particle distances either become indefinitely small or grow to infinity, that is, the system of point masses is unstable and it must disintegrate. The integration of the Lagrange-Jacobi formula with respect to the time shows that the integrating or averaging of the moment of inertia over an interval of time can also be applied in the proof of the Virial theorem for mechanical systems. In order to perform the averaging of a physical quantity f over a long or even an infinite interval of time, that is, determine the mean of f as a function of time t over a period of time tau, we define its time average by 1 over tau times the integral of the quantity f from 0 to tau with respect to the time t, where tau tends to infinity. By applying the Newton-Leibniz rule, the mean of the function f over the period of time tau can be written as 1 over tau, times the difference between the function capital F evaluated at tau and 0, as tau tends to infinity. Here capital F is the primitive function of the function f. Then the average of the quantity f is determined by the behavior of the primitive function at the limits of the time integration. If the difference in the brackets is bounded, then the limit in the averaging is equal to 0. If the difference diverges on the order of the time t to k as tau tends to infinity, then the exponent k will determine the result of the averaging. If k is less than or equal to 1, then 1 over tau times the difference is bounded, otherwise the average of f over an infinite period of time is divergent. We will show some examples of the function f of time which can be averaged over an infinite interval of time. For a periodic function, for example a times the sine of b times t with the graph in red, the limit of the integral divided by the period of time tau vanishes. One can interpret this result as the integration can be performed over an integer number times the period of the function f, which always gives 0 even if the integer number tends to infinity. We can also consider a times the exponential function with the negative exponent minus b times t plotted in green, which has a convergent integral between 0 and infinity. As a result, its average vanishes as well. However, if its exponent is positive as seen in the yellow graph, then the integral of the unbounded function growing faster than tau gives a divergent average. This is the case for linear functions like a times t plus b plotted in blue as well, since its integral is the order of tau squared. The function a times the natural logarithm of b times t seen in magenta graph has a similar behavior as its integral grows faster than tau. If we average Lagrange's identity over time, then we need to evaluate the average of the second-order derivative of the moment of inertia I with respect to the time t in the left-hand side of the identity. When integrating the left-hand side with respect to the time t, we apply the Newton-Leibniz rule and subtract the primitive function of the second-order time derivative of I, that is its first-order time derivative evaluated at tau from the derivative of I evaluated at 0, where tau tends to infinity. For a system of point masses performing a periodic motion, it is enough to integrate the acceleration of the moment of inertia over the period of the motion of its particles. Then we obtain the same values for the derivative of I at the beginning and the end of the period, and their difference vanishes. If a non-periodic system is bounded and its particles go in regular orbits, the moment of inertia of the system will oscillate regularly between two finite values. Then the derivatives of the moment of inertia evaluated at the initial time 0 and at any tau are finite as well, and their difference is bounded. Since it is divided by tau, it vanishes as tau tends to infinity. As a result, the time average of the left-hand side of Lagrange's identity is equal to 0 for a periodic or any bounded system. The vanishing time average of the second-order time derivative of the moment of inertia of a self-gravitating system describes some kind of quasi-steady state in which the system is in a dynamical equilibrium. We can formulate the result of the averaging of Lagrange's identity in the Virial theorem proved by Clausius in 1870, stating the time averages of the kinetic and potential energy of a stable conservative mechanical system are related by the following formula. Twice the average of the kinetic energy over a period of time is equal to minus the average of the potential energy over the same period of time, or the time average of the kinetic energy is given by minus half the time average of the potential energy. The period of time must be long enough so that the averaging could provide the mean kinetic and potential energy of the system. The Virial theorem is a fundamental relation between the kinetic and potential energy of a mechanical system, and it is valid for a wide range of natural phenomena that is governed by the action of different physical interactions between the constituent particles of the system. For stable non-conservative mechanical systems where no potential energy can be defined, the Virial theorem still holds, stating that its averaged kinetic energy of the system over time is given by minus the average of the virial of the system over time. Or as Clausius stated, the mean vis viva of the system is equal to its virial. This form is very important in the kinetic theory of gases, where the gas is not considered as a continuous medium but a many-particle system formed by the atoms or molecules of the gas. In other words, both the forms of the theorem tell that if a stable mechanical system reaches a quasi-static state where it is in a dynamic equilibrium, then its average kinetic energy is equal to minus the average of its virial or potential energy. Such a process whereby a self-gravitating system attains stability is called virialization, and the system is said to be virialized. If we do not restrict our attention to gravitational interaction and study the general case of stable conservative systems with potential energy that is a homogeneous function of degree k, then the Virial theorem states that twice its averaged kinetic energy over a period of time, minus k times its averaged potential energy over the same period of time vanishes. For closed systems the law of conservation of energy always holds, therefore the sum of the time average of the kinetic energy and the time average of the potential energy is equal to the total energy of the system, which is constant. Let us summarize the content of this presentation on the mechanics of systems of point masses. We started with the introduction of the concept of a system of point masses, and we described its equations of motion in Cartesian and curvilinear coordinate systems. We also distinguished between free and rigid systems of point masses and classified the forces that can act on such systems as internal and external forces. Based on this classification, we proved the law of conservation of momentum for a system of point masses, stating that the derivative of the linear momentum of a mechanical system with respect to time, that is its rate of change, is equal to the net force of all the external forces acting on the system. The conservation of momentum follows from this relation and tells us that if external forces do not act on a mechanical system or the net force of these forces vanishes, then the momentum of the system is constant and its center of mass remains at rest or in uniform linear motion. As a consequence of the law, we found that the center of mass of a mechanical system moves as if the total mass of the system were concentrated at the center of mass. We also presented some examples illustrating the conservation of momentum in mechanical systems such as the solar system, an exploding grenade, jumping, a cannon and its projectile, and the principle of propulsion. We define the angular momentum of a point mass with respect to a given point by the cross product of the position vector of the point mass relative to the point and the momentum of the point mass. By proving the law of conservation of angular momentum for a system of point masses, we established that the derivative of the angular momentum of such a system with respect to time is equal to the torque produced by the net force of the external forces acting on the system. As a consequence of this statement, we saw that if no external forces act on a mechanical system or the torque produced by the external forces acting on a mechanical system vanishes, then the angular momentum of the system is constant. We also introduced the moment of inertia of system of point masses with respect to an axis of rotation as the sum of the product the masses of the particles and the square of their distances from the axis. This helped us to express the component of the angular momentum of a rigid body along its axis of rotation by the product of the moment of inertia of the body and the component of its angular velocity vector along the axis of rotation. As the demonstration of the conservation of angular momentum, we presented different experiments such as a student sitting on a revolving stool and changing her moment of inertia by moving some weights and manipulating a spinning wheel. We reformulated the work-energy theorem for a system of point masses by introducing the total kinetic energy of the system as the sum of the kinetic energies of the individual particles and stating that the change in the kinetic energy of a mechanical system is equal to the work done by the forces acting on the system. We also demonstrated that the kinetic energy of a system of point masses is the combination of the kinetic energy of the total mass of the system concentrated at the center of mass and the kinetic energy of the system determined in the frame of reference of the center of mass. By applying the work-energy theorem, we proved the law of conservation of energy stating that in a conservative mechanical system the sum of the kinetic energy and the potential energy, that is the mechanical energy of the system, is constant, if any constraint imposed on the system is independent of time. As a general example combining more laws of conservation, we talked about the collisions between homogeneous spheres performing translational motion, and classified them based the positions of their center of masses and the direction of their velocities relative to the direction of their impact. We distinguished between central and eccentric collisions, and between head-on and oblique collisions. We also had a classification based on whether there is any loss in the kinetic energy of the colliding body due to their deformation and distinguished between perfectly elastic and inelastic collisions. We discussed perfectly elastic and inelastic head-on collisions and perfectly elastic oblique collisions, and determined the velocities of the bodies after their impact in such collisions by applying the laws of conservation of momentum and energy. Then we considered real collisions and defined the coefficient of restitution by the ratio of the change in the velocity of the bodies in real collisions to the same change in perfectly elastic ones. This coefficient was used to determine the velocities of the bodies after their collision in a realistic scenario. As an application, we presented the working principle and the procedure of measurement of the velocity and impulse and of a projectile or the force of its impact with a ballistic pendulum. In our last topics we generalized the moment of inertia of a system of point masses about a point, and derived Lagrange's identity in the Lagrange-Jacobi formula stating that half the acceleration of the moment of inertia of a self-gravitating system is given by either 2 times its kinetic energy plus its potential energy, or twice its total energy minus its potential energy. We also proved Jacobi's theorem stating that if the total energy of a conservative system of point masses is positive, then at least one of the mutual distances between the point masses will increase to infinity as the time tends to infinity. Finally, we presented the proof of Clausius' Virial theorem stating that the time average of the kinetic energy of a stable mechanical system is equal to minus the time average of its virial, or minus half the time average of its potential energy.